Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Know-How is brought to you by CacheFly.
This episode of Know-How is brought to you by GoToWebinar, a trusted webinar platform with over 55,000 customers who have hosted over 2.7 million interactive web events to connect with their audiences. For more, visit gotowebinar.com/podcast. Today on Know-How, it's the best of 2017. Welcome to Know-How. It's a Twitch show where we build, bend, break, and upgrade. I am Father Robert Balaser, the digital Jesuit, and you may notice that we're not at the radio corner this week. That's because this is a special show. This is the best of 2017. Now, 2017 has been an interesting year. So many topics, so many projects, everything from how to grow to how to program to how to 3D print and even how to break things, because that's what we're really good at. But we decided to put together a little episode that might take some of my favorite segments and some of yours and put them into one place for easy-to-reach reference. One of the most important topics, and really the most popular topics that we've covered all year, has been networking, specifically our Networking 102 and 101 series, where we gave the very basic concepts of the connected world to you. So without further ado, this is Networking 101. We got to talk about the basic, the thing that we're all going to need if we want to be on the internet, and that is
a modem.
Well, yeah, but
pay for Comcast.
That comes from your provider.
Oh, right.
The router.
Oh, yeah.
But actually, I'm glad you brought that up, because in a lot of cases, the modem and the router are the same.
And in those cases, I usually hate them, especially if the case is Comcast.
Yeah, it used to be that your provider, be it your DSL provider or your cable provider, or back in my day, your, ISDN provider,
wow,
your T1 provider, they would give you what was essentially an entrance into their network.
And that came on like a little horse and buggy kind of contraption. They dropped that off.
Yeah, it was dropped off by storks and pelicans. It's,
right.
Oh, I got a brand new internet. No, but yeah, it was kind of slow back in my day. Thank you for reminding me that. But the whole idea was that device gave you real internet. So it was your real address, it was your real connection to the internet, and then it was your job to have some sort of device that would allow you to turn that one address or 2, 3, 4, a dozen addresses into something that you could actually use.
Okay. Well, just right before we get to the routers, because it does go from the modem to the router in most cases. The thing I have an older modem that I actually bought,
right,
and I paid for, and so it's paid for itself because I don't have to rent it anymore from the ISP. But they've been calling me, telling me I need a new modem.
You do, okay.
And I bought one, but I have not put it in, and it's still, the old one's still working. Well,
the old one may be working, but you're probably not getting the most speed. So what they've done over time is they've upgraded the version of DOCSIS. That's the communications protocol that they use in order to connect your computer to their network. The older ones will work as they're backwards compatible, but the older ones typically don't allow as many channels, as much speed, as much bandwidth.
Okay.
Now, if you're not using a lot, then you may not notice it, but I mean...
I'm locked in at 35 down, 5 up.
You could probably get more in this area.
Okay.
So you may want to do that. Yeah, I'm with you. I used to love to buy, because I didn't like paying a rental fee. More recently, I've just kind of surrendered, because
you've given up.
I've given up because, like with Cox, with my my family up in Las Vegas, they have to use Cox cable, and Cox would do something where it would require, if you bought it, you'd have to like rebuy one every 12 months, and that was annoying. It was like, well, yours will work, but you may notice dropouts, or in the worst case scenario, something happens, your network doesn't work, and now they say, well, you bought the modem and it's not ours, so we can't be responsible for it, so go screw.
It makes me so sad, though,
Yeah.
especially since they've beaten you down, who's usually the person who's the
Well,
most...
I mean, if it was my personal modem, I would absolutely do that. But I mean,
Yeah,
it's like
you don't want to have to deal with it
I
because
can't
it's
do
your
it
family
remotely.
stuff.
Yeah, I can't tell my parents, yeah, you're just not going to have the internet for the next 3 weeks before I get there.
Or, Dad, did you touch the modem or router again? Because
Because it's in the wrong side of the house, Dad. All right.
Okay.
So let's go ahead and jump into routing. Now, when we think about routing, this is the core language of the internet. This is how the internet works. I mean, a lot of people know the story of the internet. It was a DARPA project. The whole idea is, could you make a redundant sort of self-healing network, a network that could route communications from one point to another, even if you disrupt local nodes? Because before that, our idea of networking was something like token ring, where you would literally have a physical ring of computers, and it would pass a token, which was permission to speak, down the ring. And if you removed it from any of those nodes, suddenly the entire thing went down.
Wow.
Because you had an empty node on your ring, right?
Right. That makes sense, though, the early days.
Yeah, and in the early days, say, you don't remember this, but I remember when like one person would decide to move his computer, so he like pulls all the plugs out from the back of his computer, it took down the entire network.
Wow. Yeah.
I mean, we wouldn't put up with that
That
today.
is not sustainable.
No, totally not. But back then, it was like, networking was so new. It was like, oh, they're connected. Well, it's not connected right now, but when it's connected, whoa!
Pretty cool. We can send each other a message, maybe.
Well, back then, you got to remember that the network stacks are really insecure. So it was, I can take over your computer.
But then what could you even do with that computer?
No,
Make
solitaire.
Print something out on the dot matrix
You know,
printer?
I'm feeling so much hate
It's not
for
hate.
the elders
It's
of
not hate.
computing. I don't know.
I'm just trying to appreciate the nostalgia, that's all.
All right, let's get back into the nostalgia. Let's talk a little bit about what it means to route, because a lot of people, since your Magic Box has both a router and a switch, and probably wireless as well, they kind of conflate them. They think routing is the same thing as switching, and it looks like that because even the plugs are the same.
Right, I have blinky lights, just like both of them just blink at me.
Precisely. So they must speak the same. Not necessarily. Even though on the back of your consumer router, both the WAN port and the LAN ports are using Ethernet, the core technology governing each is slightly different. So when we're talking about switching, we're talking about multiple computers connected to the same switch, right?
Right.
Well, that switch needs to figure out a way to direct communications, Ethernet frames from this computer to this computer. So what it will do is it actually, that switch, the memory inside that switch, keeps a table of everything that's connected to it. All the different computers, right? Because remember, every computer has a MAC address. That's a unique, that little 16-digit alphanumeric thing.
Right.
That is unique to that computer.
Identifies it, yeah.
Right. The first time you turn on the switch and turn on the device, that registers with the port that it's connected to. It keeps it in memory. It says, oh, anytime I get communications for this MAC address, it's connected to that port.
Right, and then it also assigns an IP address to it, right?
Well, IP is later on. So IP is higher up in the stack, but at the switch level, you're only speaking in those frames, those Ethernet frames.
Oh, okay.
Here's the thing. This is great. This works really, really well because the way we used to do it was we used to use hubs. And hubs were just repeaters. So all they did was any traffic it got,
It just sent it out.
It sent out to all the ports. It's like, hey, is this any of you?
Right.
And the one computer that was was like, that's me, but everyone else could hear. It'd be like all your neighbors in your apartment building yelling at each other every time they want to talk.
Okay, yeah, that would be irritating.
Irritating.
And it would be insecure, yeah.
Very insecure. And what a switch will do, a switch will actually, after the first time, once it's registered who is whom, when your communication frame goes out and it says from this computer to this computer, it will only deliver to the port to which that computer is connected to. And so it'd be like picking up the phone and actually dialing someone in that apartment building. Much more efficient, and it seems like, oh, that's a great way to communicate.
Yeah, totally.
Except this. What if you're not connecting 64 apartments or 100 apartments or even 1,000 apartments? What if you're connecting like 100 million apartments? The table that you would have to maintain to know where everything goes would be unimaginably large. It's just, it's unserviceable.
Yeah, and then try and search through it to find the one that you need. Yeah, that would be insane.
Yeah, you can't do it. So we have routing. Routing is not switching. They look the same if you're just thinking about, well, I connect to this, I connect to this. But routing, rather than using a table, a complete table of everything that's connected, instead it has what are called route tables. So it's like,
So like a subset?
Kind of, exactly. It's I don't know exactly. Let's say I want to go from this computer to this computer. and it's connected from here to here. That's connected to this one and this one. That one's connected to that. That's connected to this one. That over to there. Some weird, right?
It's a weird web.
That's how the internet is. The internet is just this weird interconnection of different networks.
Right.
But what routing will do, specifically BGP, Border Gateway Protocol, it will allow me to not exactly know where the computer is that I'm trying to communicate, but to know enough that I think it's probably in that direction.
Okay.
So all of these routers will keep at least a little bit of the direction, the map that packets need to be sent in order to reach their destination. And so we'll go from here, it'll say, look, I'm looking for 10.50.50.50, and this one will say, well, I don't know where 10.50.50.50 is, but I know where 10.50 is, and then we'll send it over here, and then it's the same question. Maybe that goes to there, then it goes over to here.
Right.
That's how routing works. This is super simplified, by the way. If you want me to get crazy complicated, you got to watch my other show, This Week in Enterprise Tech. That's not what we're here for. But in a nutshell, that's the difference between routing and switching. When I'm routing, I'm going between networks.
Right.
When I'm switching, I'm going between devices on the same network.
Okay, that makes sense. I can knowledge absorb that. I mean, I do have a question about, is that what DNS is then?
Yes.
I don't want you to have to go too deep.
No. This is important because DNS has recently become very important because people are attacking it.
Right.
I don't actually need DNS ever if I know the IP address. So if I know the IP address of a server, like I used to have a block of IPs that are memorized because they were mine and I had servers on them. Or for example, like OpenDNS is 208.67.220.220. Google DNS is 8.8.8.8. Yeah, so there are a couple numbers that you remember, but those are all IPv4, by the way. We'll talk about that in a little bit. What DNS does is it allows me to have a service that when I type in Reuters.com, I don't have to remember that Reuters is 12.13.52.12.
Right.
It actually looks it up. It says, hey, what is Reuters? And it will say, oh, Reuters is this IP address, and then that's what it sends out. So when I'm talking to another router, I'm not saying, where's CNN, or where's Fox, or where's Banggood? I'm saying, where is this IP address? DNS allows me to resolve a name back to the IP.
Okay, so it's kind of like a routing table.
Yeah, it's the same idea. You keep a table of what is what.
Okay,
Right.
cool.
So that's routing. And it's important for us to know this because that device, that magic box, is part switch and part router. Those LAN ports are all switched.
Right.
That WAN port, that's actually that's a routing port. That's connected to another network. That connects your network
to the world network.
Well,
the World Wide Web.
The network of your ISP, which is connected to the world. You got to remember, this is all layers and layers of connectivity.
You're right. It's an onion of internet.
And like onions, they make you cry.
There's a few ogres out there too.
Yeah. Okay, so let's get back to the basics. We've already talked about what a switch will do. We've talked about how it keeps a table. We've talked about how routing actually jumps from network to network until it reaches its destination, and then it can come back because it kind of has a map already, right?
Right.
But here's the fun thing. With this, because everything is interconnected, if I lose a node, there should theoretically be enough interconnectedness between all the different networks that make up the internet that I can still find a path. It may not be the shortest path anymore, but I should still be able to go around any damaged or unresponsive node of the internet. Okay,
so it's kind of like a redundancy plan or something.
Yeah, well, that's what it was built for.
Cool.
Yeah. So when we're talking about routers, there's a couple of different ones. There's the edge router. That's what we have. And it's think of a network as a big circle. The edge, it hangs off the edge, right? So those are the little edge routers. Those are me, right? Like, this might be my ISP.
Right.
All the edge router is designed to do is it's designed to take the routed traffic and turn it into something my network can understand. But then we take a step back up from the edge, and from the edge you get the subscriber edge, and that might be like Comcast. Or AT&T.
Or Cox.
Or Cox, right? So the subscriber edge routers are designed to connect to the edge routers. Go one more step up, and now we have the border routers. The border routers are, well, they're the ones, the big iron, that connect across networks. So imagine this. Imagine your router has to carry your traffic, right? Go a step up.
So then ISP router has to handle all their subscribers' traffic?
Right, precisely, exactly. So that subscriber edge has to handle all the traffic of all the edge routers connected to it. So it has to be a bit more, well, actually a lot more powerful.
Okay.
Go a step up. The routers that connect subscribers together. And
Yeah.
remember, those subscriber routers are connected to all those edge routers. They have to be really big.
Yeah.
And they have to have a lot of power and a lot of memory to be able to handle that, right?
I'd like to see one of these facilities.
I've got one if you'd
do?
like.
Yeah, okay.
And then you go one more step up, and it's now we're kind of splitting hairs. We're talking about the backbone routers, and these are the big boys from HP and from Cisco and from Huawei. And all they do all day is route all of the traffic between, like it's to which the internet is connected. It is
Wow.
basically the internet.
Interesting.
Yeah, right.
I want to see these actually.
Oh, good. You could
Maybe
watch
someday.
This Week in Enterprise Tech.
Yeah? Is there a
Friday,
show that
1:30.
would
Is there a
talk
show
about
on the
this?
Twit TV network that talks about enterprise technology?
No,
Couldn't
it would
be.
never happen. It would never happen.
No, sorry about that. Okay, but we're not talking about that stuff. We're bringing it in just so that people understand you're one little piece of a huge, huge network.
Right.
But let's talk about what your router does, because your router is different. It is a router, but it's a router with some built-in functions for consumers.
Right. Right.
And there's 4 main functions that you have to think of when you buy a router. The first is NAT, Network Address Translation. The second is DHCP, Dynamic Host Control Protocol. The third is the firewall, which is actually linked into the NAT functionality. And the fourth, and this is actually relatively recent, wireless.
Okay.
So those are the 4 pieces that we kind of expect. When we buy anything from a budget router up to the high-end router for the home, it's got to include those 4 pieces.
Okay, yeah, that makes sense. Because you just want to connect the devices that you have at home. And if you've ever had a gaming console, you've probably run into a NAT problem before.
Exactly. So let's talk about NAT. NAT is Network Address Translation. Some people don't know why we have NAT, and again, the older people will. And the reason why we have NAT is because back in the 80s, I know, the world existed.
80s, you say?
80s.
Oh,
Yeah,
okay.
We were alive.
There were people before me?
Young people. Okay, back in the 80s, IPv4, that's the IP addressing, that's the scheme number 4, which was based on 4 octets.
Right.
Basically, 256 values, 256 values, 256 values, 256 values. Well, multiply that, you get a whole lot of possibilities. And we thought, that's so much,
You'll
we'll never
never
need
run
that.
out, yeah.
It's, back when the internet was still really, really small.
Right.
And we were able to, for example, I owned a Class B. I owned a chunk of the internet. And they just gave it to me because we were a company and we did some research. And I gave it back, but I shouldn't
Right.
have, because the thing would have been worth millions. But you got to remember, back then, every device we connected to the internet was actually connected to the internet. You could see it. It had a real IP address.
Okay.
Because that's what we did.
Right.
Because we had so much space, we're like, well, why would we do anything else?
Right.
Towards the mid 80s to early 90s, we started hitting what was called IPv4 address exhaustion. We had handed out so many addresses, and most of them weren't actually being used, that we were running out.
Right.
And people were thinking, okay, we're going to have to switch to IPv6. It's the one that we're using now, which has enough addressing space to give an IP address to every atom in the universe.
So we'll never run out again.
But no, this time we really won't. Seriously,
This time we won't.
We really, really won't. But what we did, instead of switching over, because we're like, oh, well, I don't want to replace all my equipment.
Yeah.
All my equipment was designed for IPv4. If I do IPv6, I have to replace all my switches. I have to make sure that all my computers can be stacked that way.
Right.
We did what was called NAT, Network Address Translation. It was recognized that most of your devices shouldn't have a real internet address. In fact, that was bad. I don't want people to be able to directly access my device.
Right. That makes sense. So you should get one, and then you kind of disperse that amongst your machines.
Precisely.
Yeah.
I need one real address because the internet needs to be able to address my network.
Right.
In order for me to be a router
talk
on
back and
this,
forth, yeah.
I have to talk back and forth. So I need one real address. But once I've got that one real address, that device, which is my router, can talk to all the devices behind it. They don't actually need a real world address.
Right, right.
And so what this meant was I could take a single address and I could turn it into as many computers as I want, any nodes as I want.
See, that makes sense, because if, like, the way I'm imagining it is if you had a house, like, you would just have one door to go into the house, and then that's where you have all your stuff, instead of just like a bunch of doors leading to all the different rooms of your house from the outside.
Yeah, and there was good for security, because it meant that if you were trying to hit my network from the outside world, you could see that one device, but you couldn't see anything else behind
Past it.
Yeah.
Okay.
Yeah,
So,
right?
all right, then that helps take care of that. But what is an open NAT versus a closed NAT?
Oh, we'll talk about that when we get to firewall. Don't worry about it.
We'll get to that? All right.
Because there needs to, sometimes I do want the internet to be able to hit a device behind that layer.
Right, especially if it's a gaming machine that you have to, talk on different ports with.
Precisely, and so we'll talk about that when we get to firewall. But first, I want to go to one of the other features of your router that most of you probably don't realize is there. Maybe you've heard the name, but you don't know what it does. It's called DHCP. This is really, really important. Again, back in the day.
Can we just go black and white whenever you start talking about that?
Put some lines across the screen.
Make it look like VHS.
Yeah, change the vertical hold just to make sure we stay in place.
Vertical hold?
But you got to remember, when we all had real addresses, before DHCP, I had to know all the information for my addresses. I had a notebook. It's not a computer. I had a notebook.
Oh, that's sad.
Like with pencil that listed my range, and it was like, okay, which MAC addresses have I associated with which addresses? That was
wow.
It was a crazy fancy system.
Oh, I bet, yeah. And then you carry your notebook around with you everywhere.
Oh yeah, and if you lose your notebook, you just lost your table.
That's bad.
No, but what DHCP does is it allows a computer, a node, a device to request an available address from a central authority that will work on that network. And so what it needs to be able to do, it needs to keep a table to make sure that it's not giving out an address that another computer is already using.
Right.
And it also needs to make sure that every once in a while it expires those addresses so that the clients will request a new one, just so it could keep it refreshed. Okay. In the old day, you don't see it much anymore, but back in the Windows 98 days, 95 days, people were so accustomed to seeing a little window pop up saying, that IP address is already in use. Contact an administrator. And it's because someone else has jumped onto your IP. And it was a cascade. Okay, we're totally getting off the rails. But there was a cascade effect. The people who knew just enough to know where to change that, they're like, well, someone takes my IP, I'm going to jump on another IP. And then it would just down the chain. Everyone's like,
wow.
I'm knocked off. Hey, who's on
It was
my
snowball kind of effect.
Yeah, and so you'd have administrators who are under no circumstances are you to change your IP address. If you have a problem, you call us. We'll come over and see what happened.
Okay. So if two machines were trying to use the same IP, then just one would be able to access and the other one would just be like, I can't be addressed to the internet kind of situation?
Well, the last one to request, or the last one to take it, would actually have priority.
Son of a gun.
But you got it's the way that it works. Basically, the computer screams at the switch.
Yeah.
Says, I am this. I am this. And so all the traffic will be directed to that. And if you have two that are trying to both claim that I am this, whichever one did it last gets the traffic.
Okay.
That's
Me.
Yeah, basically.
Yeah. Okay.
And actually, that's an attack. That still works, and we'll explain that next week.
Wow.
Yeah.
This is cool.
It is cool. DHCP it's actually a quick process. So we go from discovery. And so when you plug in a computer, the very first time it connects, it does what's called a DHCP discover. So it sends out, it's a broadcast message. So let's say my network is 192.168.1.1. That's my router. It's going to send that 255.255.255.255. And that is the special address. That means it's going to send it to everything on the network.
Isn't that usually, is that called the subnet mask or something?
Well, that is a subnet mask, but this one's this one's called a broadcast address.
Okay.
And so when I'm sending something to that, everything on the network is going to get it, and it's basically the client saying, "Hey, I'm new here. Could I get an address, please?" And it will wait. And it will wait for someone to give what's called an offer. So you have DHCP discovery, then you have offer. And the offer is the DHCP server saying, oh, hey, okay, did you want an address? Was that you requesting an
That
address?
was me over here. That was me. Yeah.
And then from that, it's gonna the client is gonna do a DHCP request. So it's no longer a discovery, but it's a request, and the client's saying, yeah, that was me. I need an IP address, and then the server should acknowledge it's a DHCP acknowledge,
Right.
sending back to the client. Okay, this is the address that you can use.
Right.
so-
So that's happening all automatically.
That's all automatic. It's a 4-part process that, I mean, you take it for granted.
Right.
It did not always exist, and it was so much better once we got it.
So before that, before DHCP, would it have been what you would call a static address, where you had to, this is the IP for, yeah, okay.
Yeah.
Because I've had to do static IPs before.
Yeah.
And that just means that machine always gets that IP address, right?
Precisely. Or because sometimes, I mean, we'll explain this when I get to next week's episode when we actually set one of these things up. But what I will typically do is I will have a range that DHCP pulls from, and then I will have a range that DHCP doesn't touch. And I know those are my statics. But I got to maintain my statics. If I drop 2 on top of the same address, it's going to be the same problem that we had back in the day.
Okay, smart. I like that idea. Because, yeah, the issue I would have is I'd turn off a machine and then turn it back on, and it would have a different IP if another machine had taken that. Yeah.
Fun stuff, right?
Okay.
Grrr. All right, so we go from that. The third feature that you're going to expect is a firewall. And you hear this all the time. I've got a good firewall.
Yeah, it's impenetrable.
Do you know what the firewall actually is, Brian?
I imagine like a Tron situation where it's actually just a wall of fire and the little motorcycles can't get through it. Isn't that what it's like?
Actually,
Is that it?
Thank you. We're
Sweet.
done. Thank you, ladies and gentlemen. If you need to know more, please go to our show note. No.
See, all the inner workings of computers just go back to Tron for me. It's just little people and motorcycles going around, which I like to think about.
Yeah. Now, the firewalls I deal with are actual firewalls. I mean, like I have one.
Walls of fire.
Well, yeah. With propane. Yeah. No, but I've got like Sonic Wall, which was Dell. Now it's Sonic Wall again. Those are enterprise class firewalls, which can look at every single packet, and I mean, they're really good with rules. The firewalls that we build into consumer routers, yes, technically, they are firewalls. They are firewalls. They're not that advanced. Typically, what they are is they're paired with the NAT, the address, a network address translation, to enable and disable ports.
Right, because all the ports open would be bad.
That would be bad. Yeah, we don't. That's what it used to be. It used to be when you would plug your computer into the internet, everything was open. It was just like,
because it's
I trust you.
It was like a 1950s happy, like Leave It to Beaver neighborhood,
Do you
right?
compare everything to TV?
Sometimes.
Okay.
Yeah, the things I see on TV, yes.
No, so in your consumer router, your firewall will basically allow you to open and close ports. Like for example, for your gaming device.
Right.
You would tell that any traffic I get, the router, so I'm talking my router, any traffic that my router gets on port 8862 will get forwarded, and I make a rule, a firewall rule, a routing rule, will get forwarded to the inside of the network to the device that is connected at 192.168.1.5, which is a non-routable address. That address can exist in the real world, but it does exist in your network.
In my network, yeah.
Right. And in that case, because there's 65,536 different ports, of which I have access to about 65,000 of them.
Yeah, whatever.
Yeah, I have a lot. I can make rules, firewall rules, routing rules, that will take all those different ports and route them to any address I want inside the network.
Right. So you have full control then.
I do.
Which is
but
nice.
I do want those, we'll talk about this when we get to security. I want those to be closed by default. I don't want any ports open unless I specifically want that communication to take place.
Okay.
The other thing that the firewall will do, on better units, you get what's called Stateful Packet Inspection, SPI. It's not just the rules of where traffic goes. It's looking at the packets for maliciousness, malformed headers. The nicer routers, like the Synology that I'm using, can actually see attacks. It knows what an attack pattern looks like.
Okay.
And it will try to keep that traffic out.
So it's So I'm imagining, all right, here's my little, I'm imagining the packets coming through the router, little dump truck. It's like going through and there's like key items or there's like filters that it looks at and it's like, oh, this is something I recognize. That's like a bad thing.
Yeah, exactly. And again, it all depends on the power. Some routers, when they say they have stateful packet inspection, what it really means is the router's going, yeah, that's a packet. Yeah, that's a packet. That's a packet. Oh, yeah, that's a packet.
As they just blow by.
Technically it is, but it's not.
So is that really like CPU intensive? Like, is that something? Yeah. Okay. And so if you do, I guess you would have to have a nicer one to.
You'd have to have a nice one, or one that
notice a slowdown.
Has built-in silicon. Like when I was still doing interop, I worked with a company called cPacket, and that's exactly what they did. They made custom silicon that could look at every packet in a 10 gigabit connection. Which is a lot. That is a crazy amount. And literally, they could say, search all of these packets as they in real time, as they come in. Don't store them up, but as they come into the network or go out of the network, search for anything that says password. And anytime you see a packet that contains the word password, stop it.
Okay.
And I mean, it sounds simple. That is an amazing amount of processing power that you need to do that.
And to do it quickly, right?
It's got to be real time. You can't. I mean, it'll add a tiny, tiny, tiny bit of lag if you have the right hardware. Otherwise, it will just slow you down incredibly.
Okay. And you had said malformed header. I'm just kind of curious. What is that?
As I can actually, so when I'm communicating, I'm setting off a packet of information, I can compromise someone's poorly configured system by sending a malformed packet that when opened by the router, will do something different than what it expected it to do.
Okay.
That's the most layman terms explanation.
Explain it to me like I'm 5, Padre.
Okay, so the packet comes into your network and it tears off its disguise. It's like, I'm Old Man Withers and I'm stealing your gems.
Curse you, old man. Okay.
And of course, the last part is wireless, which we know what that does, and we're going to cover that when we get over to that part of the Networking 101.
Okay.
But in a very long nutshell, in a 30-minute nutshell, that's what your consumer level router does. And the reason why we did all this, and the reason why this is important, is because you need to understand when you buy that box, you're actually buying at least 4 different devices that back in the day we had to get individually.
Right. It's all in one, and it's probably a lot cheaper than it used to be.
It's a whole lot cheaper. But I mean, it also means that, there were some sacrifices to get everything down in that package. I mean, we used to have to configure our own routers. We used to have to build our own NAT box. We used to have our own DHCP servers. We used to have our own firewalls, and we had separate access points that we would set up.
Right.
Now it's all contained within one box, but you still have those discrete components in there. You need to know what they do, and you need to understand what's running because you're going to configure your network the way that you want. That's how you get a high-performance, low-cost network.
Pretty cool. I think it's fascinating to know all the different components, but one last question I kind of have about firewall is, isn't there like hardware firewalls and software firewalls?
Yeah, and that's exactly what I was talking about. Hardware firewalls have custom designed chips. Like SonicWall, they build their own silicon. cPacket, they build their own silicon. Even the failed startup that we had not too long, Guardian, remember Guardian?
Yeah.
That was a custom ASIC that they had designed just for throughput, because you can design chips just to do one function really, really fast. So instead of, the problem with the software firewall is most of them run on general purpose CPUs.
Right.
And that means they're never going to be as good at their job as a custom design ASIC, because they've got all this overhead that the custom design ASIC doesn't. It's like when I'm running a software firewall, I'm running it on top of a CPU that could do everything. It's the happening guy. I could be a fireman, I could be an artist, I could be a cop.
Right.
I can't be any of those things exceptionally well, but I can do everything.
Okay.
The custom ASIC is like that guy who's like, I sweep.
And that's
really good at sweeping.
Yeah, like instead of being a jack of all trades, you're the master of sweeping.
Precisely. So you take silicon and you have it so that all it does, like the cPacket example, is it does SPI. It can open the packets, look, and send them off. Open the packets, look, send them off. That's what it does. Does it very fast. A bit more expensive, but performance, I mean, you can't compare them.
Okay. Now I'm thinking, because there's Windows. Windows has firewall built in, right? Or
That's different.
is that different? So
That's
it's not like I want to go into my router and turn off the firewall settings in there because I'm like, oh, I already have a firewall on my computer, so why would I need to double up?
Yeah, the Windows firewall, that's basically just port blocking.
Okay.
It just makes sure that the services are off that shouldn't be on.
Okay. And then asks you, like, do you really want to open this port? Or
It's good. It's not like junk.
Right.
But they're both firewalls. They just do slightly different things.
Okay. Cool. Cool.
Now, ports are important because you, at some point, are going to want things on the inside of your network to talk properly with things on the outside of your network. Now, in most cases, that's not a problem because the device on the inside of your network can reach out and initiate a conversation. But sometimes, just sometimes, you need a way for something on the outside to reach in. That's when you have to understand ports and port forwarding.
Right. You just open all the ports, and that way everything can talk to the internet.
Wow. The scary. Here's the funny thing. I understand what you're saying. I know that's a joke, but
I'm being sarcastic.
In the old day, that's what it used to be. Remember, we talked about NAT and what it was like when everything had a real address on the internet.
Right.
We didn't know about things like security. We just knew you plug this in and suddenly I had access to my Netscape browser. Yes, that was a thing back then.
Netscape
Stop.
browser.
Don't even go there.
Did you search on Alta Vista too?
I Gopher.
Yeah. Gopher.
You don't even know Gopher, do you?
No, I don't.
Okay.
I'm trying to make a joke about Alta Vista, and I don't even know what Gopher is.
Well, back in the day, anything that was running on your computer that was a network service had to open a port. And a port is it's a construct. It's not a physical thing. It's not like a network port you plug something into. It's just a way to set up in the TCP/IP layer a little thing that listens. And it listens for a request. That's a port.
Yeah.
Right?
Where like a ship of data will come and dock. Is that not a good metaphor?
Okay, no, that works. Okay,
Maybe.
yeah, you keep the port open so the ship can dock and unload its data.
Cargo, yeah.
Yeah, all right.
I don't know.
Yeah, we'll go with that.
That's why I thought they were called ports. So every time I come back to networking, it's little light cycles, it's basically Tron. Tron in my mind. There's little motorcycles that
and
pass.
pirates, evidently.
Well, yeah, of course. There's going to be giant pirate ships that come and drop off cargo at different ports.
And there you have it, folks. Today we're talking about data pirates.
That's right.
All right, so when I'm talking about these ports, what I'm talking about is it's a 16 bits worth of unsigned values. And that means there's 65,536, so 2 to the power of 16.
Okay.
65,536. We don't use port 0, so there's actually 16,535 available ports for me to address.
I'm going to have to take your word for that.
Okay, it's math. You can do the math later on.
We're going to have to check this math
We'll have to check the math. But it's not as if there are just those 65,536. There's actually two main ways for devices to talk across the internet. There's TCP, Transmission Control Protocol, and UDP, which is a Uniform Datagram Protocol.
Okay.
Yeah, so the reason why that's important is because there are different ways of communicating that have very specific strengths and weaknesses.
Okay, good. I need to know the difference because when I set up port forwarding for my Xbox, there were ones that they said to do TCP and ones they said to do UDP, but I'm not sure why.
And most of the time, they actually just say set both UDP and TCP.
Because is UDP back and forth and TCP is one direction or something like that?
Kind of. Yeah. Yes, that's a very good way to think of it. So when I'm thinking of TCP, I'm thinking of a two-way conversation where there's a handshake where two clients or two computers, two nodes, decide they're going to talk to one another. Okay, it's like, hey, and exactly, and it stays as long as that connection stays open. We're shaking hands, and I'm saying, hey, I'm going to give you this piece of data, and you're going to say, I've received the piece of data. Then I said, I'm going to send you the next piece of data, and you say, I didn't get that, and say, okay, I'm going to send it back to you. Right. So
and then I get my hand back.
So it's a very good way of making sure that the communication is actually taking place. But there is a weakness, and the weakness is that you have to establish that connection, you have to handshake, and you have to maintain that connection, otherwise you have to reestablish the connection.
Okay.
It's very good. Normally that's what we want, because we don't want to lose any data.
Right.
UDP is different. UDP, it just sends. And it can send the packets out of order. It can send them in any order. It basically looks for the fastest possible way to get from one port to another, one node to another.
Okay.
Now, this is good
if you don't worry about losing a couple of packets here and there. Like, for example, if you're streaming video, multicast video to a lot of different clients, you don't want to have a handshake to every single one of those clients. Let's say you're serving out 1 million of them.
Is that what adds to like latency then? Or
Yeah, absolutely. And that would just overload your server.
Okay.
But if you're using UDP, you can say, look, I'm going to send out a solid stream. And what you get, you get. And if you don't get something, you just miss that particular part.
And if that data isn't received on the other end, is that when you get like video cutout or like bandwidth restrictions or something, like where the video starts looking blocky?
Yeah,
in this
you
example?
can be, yeah. So if anytime there's missing data, normally your client will try to make up what went there.
Right, okay.
Yeah. So TCP, again, Transmission Control Protocol, and UDP, actually I call it uniform. It's a user datagram protocol.
Okay.
And each of those has 65,535 possible ports. So in your router, when you're setting ports, forwarding, UDP, TCP, you can choose one or the other or both.
Okay.
But you have to choose the right ones for whatever service that you're using.
All right.
Okay, so that's an overview. Let's go a little deeper, because I know that this can be a little confusing.
Okay.
So if this is the internet right here,
that's when you should get scared, is when you go over to the board.
Because my drawing is horrible. Oh, this big eye, that's the internet, right? Now it's connected to my router, which is right here. And so I'm going to say that this is my Synology. This is my RT2600, right?
Right there, that little box.
This little box. And then behind me, these are different devices that I have hooked up. Let's say this one's my Xbox, this one's my laptop, and this one's a network camera.
Sure.
Okay. Because of what we talked about in the previous week with our firewall and our NAT, network address translation, this cannot speak to this without somehow going through this. That makes sense, correct?
Perfect, yeah.
So in order for something on the internet to speak with something on the inside of my network, it has to go through my router.
Right.
And my router needs to know exactly what it's allowed to pass through and what it's not. A well-designed router will give you the ability to specifically define what traffic can pass through and what cannot.
Okay, that makes sense.
Now, in this particular case, though, here's the problem. In the old day, let's go back to my old day, each of these devices on the inside of my network would have a real, what's called a routable address. It's a real-world address. If I type that address anywhere on the internet, it would get to that device.
I see. Instead of like the IP address on your LAN.
Like at 192.168 or 10.1.14.1, which is what ours is.
And we discussed that in the previous episode
Right.
that we ran out of IP addresses, and it's a bad idea to have
It really is.
things inside your network with an internet address like
Yeah,
that.
my internet-connected toaster probably doesn't need to be connected, actually.
Your microwave does, though.
My microwave does.
Because that's got a lot of video that's going back and forth.
Well, remember, it's not just, it doesn't have to be connected to the internet. It doesn't need to be what we call public-facing. In other words, it might need to go out and talk to something, because that's what internet-connected stuff does. But there's absolutely no reason for a device on the outside to be able to hit the device on the inside.
Right.
That's what my NAT does. That's what my firewall does.
Okay.
However, if I want the internet to be able to speak to one of these devices on the inside of my network,
Then you have to open some ports.
I do, because I only have one routable address. That's the address that my router has, right? So I can't say, well, go to 52.52.1.6, because that's actually the router.
Right.
So I need a way to get from that
To the device that
to
you
one of
want.
those devices, and that's what port forwarding is going to let me do.
Okay.
So what port forwarding will let me do, let's say I set my laptop for 8088. Let's say I set my network camera for 662.
Okay.
What I can do is I can set up my router so that if any time it's single external routable addresses hit at port 8088, it will get routed to this, the laptop. If it hits port 662, it gets routed to the camera.
Okay.
So it's a way of making it accessible to the outside world without just opening up all of its ports.
Right. Okay.
Let's take a look. Does that make sense?
That does make sense. But then I'm just worried, like, okay, so if I open that port, what stops anyone else from getting access to that?
Good maintenance.
Okay.
Actually, that's a very good point. If you do open up ports, just remember that's what you've done. You've opened up a port. So anything on the internet can hit that service, can hit that port.
Right.
If the device is not properly configured, you probably shouldn't be forwarding traffic to it.
Okay.
That's like if I have a 10-year-old web server that's never been patched, I probably shouldn't put that on the public internet, no matter what port forwarding I have.
Okay. Well, so I port forwarded my Xbox, but
No, you DMZ'd your Xbox.
At one point I did.
Yeah.
Now that I have a new router, I haven't.
Well, actually, that's a good point. why not just DMZ? Because
Yeah.
I did that.
Open all the ports on
Back
that
in the
thing.
day when I was so frustrated, why can't I get Xbox Live? And suddenly there was a setting on my router that said DMZ. I'm like, yes, let's do that.
And it sounds cool too, because it's
does.
like isn't it the demilitarized zone?
Yeah,
all right.
military. I'm gonna jump out of a plane. No, but it worked. The problem is what I've just done is I've made that public address, so 52.52.1.6, whatever it might be. That public address now forwards all 65,536 ports to my Xbox. If my Xbox, for any reason, has a port that's open that should not be open,
Right.
or a service that is not properly configured, it can now be attacked by the internet.
Okay. I mean, I
don't want that.
No, that sounds bad. That sounds bad.
But let's look through some of the more common ports. Port 80, that's HTTP. So web services typically come for port 80, although we're moving away from that because now we're using HTTPS, right? We want encrypted communications. That's typically going to use port 443. FTP, which I still do. I don't know if you youngins use file transfer protocol.
I know of FTP.
Okay, that's port 21.
Okay.
So there are some givens, some ports that we kind of know belong to a certain service.
And those are like universal assigned ports.
Yeah, just universal. Well, not yeah. The thing is though, it doesn't have to be. Like HTTP doesn't have to be port 80. It's just that we all kind of agreed it's going to be port 80.
That's funny. So
FTP doesn't have to be 21. It's just that we use 21.
how does that come about? It's just
Because
everyone's
people
like, oh, we have to organize, but not really in a legitimate way. We're just gonna.
Well, because like if I type FTP into my browser and then :/ and type an address, my browser will see that and say, oh, I should probably try to communicate with port 21.
Huh. Okay.
But I could set up an FTP server on port 60,000.
It doesn't matter.
It doesn't matter.
Okay.
In fact, some people do that to try to obfuscate their ports. So they'll put FTP on a port other than 21 because people know to try to scan 21.
Right.
That doesn't really work though because my scanner will scan everything. It's
Right. Okay. So
we'll talk about that later too.
I just had a flashback to when we were at Black Hat and we were watching when we were learning about how they hacked into the Jeep.
Yeah.
And one of the things they
That
did
was
was
port 21.
scanned all the ports. And
Yep.
they're like, why is this port on here?
And that's it's a necessity. And they knew exactly. What you're talking about, of course, is when Valasek and Miller got into the Jeep Cherokee's onboard computer going through the internet connection.
Right.
Because they had a new feature that allowed you to make the car a hotspot.
Exactly.
And what they found was they were using standard ports that weren't protected.
Yeah.
So when they scanned 21, they knew that's probably FTP. When they scanned port 80, it was probably a web server. And so they could run those types of attacks against those ports.
Okay. Okay. Cool.
Now it makes sense, right?
Yeah, it does.
Good, good. Okay. So what we got to do now is let's show you precisely how this works.
Okay.
Alex, if you go to my computer, so HDMI 1, I believe. No, the other one. HDMI 2. There we go. Okay, so this is the router interface. This is my Synology R2600.
Looks familiar.
It looks familiar. I like this one. It is kind of how you say sexy. Yes.
As sexy as router interfaces get.
Exactly. So what I'm going to do first is I'm going to go to my port forwarding tab inside of my network center. This is a super, super simple interface. What I'm going to do is I'm going to create a new rule, and I can call it anything I want. The private IP address is going to be the IP address that the device has on the inside of the network.
Right. So 192.168.1. Whatever.
Whatever it might be.
Yeah.
Or in this particular case, I believe I'm 10.1.14. That's
Okay.
the address it chose. Now, the public port is the port on the real address. So that's the outside facing side of the router.
Okay.
So whatever that real address is,
Right.
it's going to say, all right, which port gets hit, do I take action?
Okay.
So in this particular case, I'm going to say, let's say it is an FTP server. So I'm going to say port 21. So port 21 on the outside, what it's going to do is it's going to go to a port on the inside. Let's say 10.1.14.31. And actually, this is cheating. This is showing me a device that's already on my network. Actually, well done, Synology. I didn't know that. So when I start doing this,
It'll bring up.
it actually
devices
brings
that
up the
are
devices that are connected to it. That's not bad.
Nice.
That's a
So
cool.
instead of having to try and memorize
Oh,
what
yeah,
IP
that's
addresses they were.
That's a cool little feature. Thank you, Synology.
Does it also have the MAC address on there too?
Yeah,
What is
does.
it? Or
Well, yeah,
access?
that's the Mac with access appended to it. But okay, here's the important thing though. right now I have set port 21 to port 21. So anything that hits port 21 on the public IP address is going to be forwarded to 10.1.14.31 port 21. But I don't have to have it be port 21. I could have it be port 6000.
Ah.
Right? So it doesn't have to be the same address. So I can say, hey,
I see.
everything, let's use a better example. Let's say port 80. So the standard HTTP address, address port. So this is a web server.
Right.
I could run 65,534, because I need one for my router, 534 web servers inside my network.
Right.
And I would just give them a different port and on the inside.
On the inside, but they'd all have the same public port, or they could?
No. They'd have different public ports on the outside. So I'd
I
say
see.
hit 8888 on the outside and hit 80 on the inside.
I see.
Right? Does that make
Okay.
sense?
Yeah, that does
and
make
this
sense.
this is normally when we're forwarding, we can forward both TCP and UDP.
Okay.
Unless you want to get really good. If the best case scenario here is to actually only forward the protocol that you're actually using.
Okay.
Most of us are lazy though, and we'll forward both because we don't want to figure out that suddenly it didn't do what we wanted to do.
Right. Come back to it later and it's broken or something.
Right. Now, so we're gonna do this in just a bit, but this is how this works.
This makes sense. It's basically, I don't know, road mapping. You know, you're giving the internet directions of where you want things to go.
Right.
Okay.
Oh, and by the way, if you do use an Xbox, I think this gets updated every once in a while, but the ports that you need to forward are 88, which is UDP, 3074, which is UDP and TCP, 53 UDP and TCP, 80 TCP, 500, 3544, and 4500 UDP.
Okay.
So
yeah, that sounds about right.
Those are the ones that, instead of doing DMZ, you can select those, forward this to the Xbox, and now everything works properly.
Right. The important part too, though, with port forwarding is to make sure that the IP address that you're using for like the Xbox doesn't change. Because the problem I did have a while back is I would port forward, but then something else would steal that IP like down the road later, and I'm like, why is my NAT closed again?
Which would be a perfect chance for you to play with statics. You could give your Xbox an address on the inside of your network that never changes.
Which I have done since then, yeah.
Which is outside of the DHCP range, so no device that connects to your network will ever try to take that address, and you know that your Xbox always has that address.
Yep.
One thing though, if you're gonna start playing like this, what you want to do is you want to make sure you document everything. Know that you set something up for a particular address and a particular port. In fact, a notebook is great. What's even better is take a couple of, get a labeler and just stick the label on the device. Because I guarantee you, it's very nerdy, but you're going to put that camera away and you're going to bring it out in a year.
Yeah.
And you're going to plug it in and you're going to, I can't remember what my username, my password, or the address was. And you have to reset the entire thing.
Right.
Just don't, just take 5 seconds and it's much better.
Yeah, it seems like you've learned from that prior experience.
Personal experience.
Yeah, yeah, exactly.
Wasn't too happy with that. What I have here is a network camera.
Oh, hey, there's a little label on there.
Look at that. See, someone takes it, but that's not actually the address. I just didn't change the label.
Oh, all right.
I'm a bad person. Okay, so
at least you remember that.
Precisely. This is an access network camera. You could substitute this for any device. Any device is going to have something of the similar configuration, and all the network stack works the same. This particular one is connected into my Synology router. Now, there's a couple of things that you might want to do that might help you in the future when you're looking at these kinds of devices. Hold on, let me get out of this. Yes. The first thing is, if you go back to here, there we go. If I go to my local network and I jump into my DHCP clients, it actually shows me all of the devices that have asked and received a DHCP address. So this particular case, I know my Axis camera, because it's got the name Axis on it. It's got the address of 10.1.14.31. That's important. That's the internal address. That's the address that has, it's on the inside of my network. So if I go there, this is my network camera. Yay!
So you just plug that IP address into your
my browser. So yeah, this is a browser. This camera actually has a web server.
I see. Because you're on your local network. You couldn't just type this in when you go to work or on a different network and it wouldn't connect. You'd have to.
Yeah. No. That address only works when I'm inside the network. If I'm outside, 10.1.14.31, that's non-routable.
Right.
If I type that into a browser and I'm not actually on the 10.1.14,
you won't be able to get to it.
I'll get nothing.
Yeah.
Right. But that doesn't have to be. All right. So let's go into the setup. If you go back to the setup for my camera here. Yes, I know, it's not private.
Thanks. And then your password is admin.
Monkey 1, 2, 3. Okay, so actually let me do this. Ooh, ooh.
Whoa!
Whoa, we're zooming. All right, so if I go to TCP/IP, this has all the settings I need. First of all, it's getting a DHCP address. But if I was going to do this for real, I would never put my cameras on DHCP. I would always give them a static because I want to know where they are. I don't want anything stepping on their address because I don't want to have that one incident and to find out, oh yeah, the camera, it got stepped on by my Xbox. So,
and so it wasn't, you couldn't get the video. Yeah, I see.
Yeah. But the other important part here is if I go into advanced TCP/IP, you'll see right down here, I have entries for HTTP and HTTPS. The camera is basically telling me what are the ports it needs to function.
Okay.
It needs 80 because that's the web server, and it needs 443 because that's SSL, that's secure. Right? So those are the two ports I'm going to want to forward
on your router.
On my router.
Ah.
But okay, here's the trick though. I'm not going to forward 80, I'm not going to forward 443 because those are really common ports. I don't want that always to go to my webcam. In other words, if someone scans and finds my router, I don't want them thinking, oh, port 80 is open, and suddenly they get to the webcam interface. That would be bad.
Okay, so you're going to just change it to a different port?
On the interface. But so I have it right now. I know that my camera is at 10.1.14.31, and I know that it needs port 80 and port 443.
443, right.
Okay, so let's go back to my Synology. And in my Synology, I'm now going to go ahead and do port forwarding. I'm going to create, and we're going to go 10. And then it fills in for me. 10.1.14.31. And the public port I'm going to say is, how about 999? And the private port is going to be 80.
I see.
So if I go to my external address, port 999, it's going to forward to the web server.
Which is 80.
Which is 80. So I'm going to create
that's what it needs to be able to connect.
Yeah.
Okay.
But I need one more, because remember, I needed 80 and
for
443.
HTTP.
Precisely. Very, very good. So 10.1.14.31. The public port is going to be... we'll call this 1000.
Oh, okay, yeah. The next one, increment up.
And 443. Although this might really screw up because now it's going to scream at me because I'm going to a non-standard port. But that's okay. We're just showing proof of concept. Okay. All right. So what I can do now is I have a second computer here. This computer is actually outside the network. So this is on the WAN port, not on the LAN port. So to that router, this computer looks like it's on the internet.
Okay. Okay.
So what I'm going to do is let me go to my status because I need to know. Oh, wait, hold on, let me save that. Let's save, thank you. Save the settings. Go to my status. I need my internet address. So my quote-unquote internet address is 10.135.25.165.
Right.
That's not a real address. That's not routable. If you tried to type that into your browser right now, that would go nowhere unless you're in that subnet, in that network. We're actually behind a NAT.
Okay.
But to my computer thinks it's the internet.
Okay.
So I'm going to go to this other computer here. So if I go to that address, which was 10.135.25.165, what do you think is going to happen, Brian?
I don't think it's going to work.
And you would be right, because that address is actually just the router. It's not the port that I set. The port that I set was 999. So what I can do is put a colon here and 999, and now it's going. See, now it's been forwarded over to the network camera.
Wow.
Right?
Okay.
There we go. Wait. So you got it right?
Okay. So this laptop that you're on right now is like. So say you're like on the internet. You're somewhere far away right now.
Precisely.
Okay. Okay.
See,
so
and now this is the computer that's on the internet. It's now going through the router, and I'm hitting port 999, which it's sending to port 80 on my network camera.
Network camera, which then you had to put in your password and stuff because that's set up on the camera.
Exact same way, exact same thing. So to this computer, all it knows is it's a web server. It doesn't care that's at port 999 because it thinks it's port 80.
Right. That makes sense. The part that kind of frightens me is what if somebody got my IP address like that?
Well, what do you mean?
And then scanned all the ports and then found...
Yes, and this is why we're going to be doing the third segment. In the third segment, we're going to explain why you should do port forwarding only if you know what you're doing. This camera, I would never put on the internet. This camera has several known vulnerabilities, so this is not something I would port forward to. I would put this inside my network and then VPN to the network, so only I have access to it. But like right now, if this was actually exposed to the internet, within 5 minutes, there'd be an automated scan that goes by it. It would see that it's open on port 999. It would enumerate it, find out that, oh, it's just a web server. It would enumerate it further and find out, oh, it's an Access webcam web server. Well, we've got an exploit for that.
Right. Okay. Okay.
Which would be bad.
I just feel like there's been times where I've tried that, where I've typed in my IP address that I have assigned at my home, and it hasn't worked. But maybe I haven't typed in the right port for it before.
It's possible. If you go back to the other computer, Alex, so what you see now is this is the traffic monitor on the Synology, and as you can see, traffic has increased because I'm now drawing from that internet, the quote-unquote internet computer.
Video, yeah.
Precisely. And see, my upload is 4.75 megabytes per second, so now I know how much that camera was taking up. If I'm doing it full resolution, that's 4.54 megabytes
if you go to
per second.
the device list too, you can see exactly what IP is taking up the data.
So if you see like my Access, almost no download, but all that is upload.
Oh, okay, that's pretty cool.
But that only happened because of this. If you go back, Alex, this is my port forwarding rules. Remember, I set it up so that if something hits 999 on the public port,
it'll be sent to
port 80
on that IP address.
On 10.1.14.31.
Makes sense.
We have to make sure we get this because this is important. Do you understand
I get this. Yeah, this makes sense.
Okay, good. Now, if I had another camera that also needed port 80. Let's say I have 3 or 4 of these things.
Yeah.
I can address them all. What I would do is I would say like 999 goes to you, port 80. 1001 goes to you, port 80. 1003 goes to you, port 80. Right? So I can have as many of those as I need because I've got 65,535 ports to play with.
Are there ports that you shouldn't use? Like, I mean, you talked about those other ones, that like FTP and stuff there.
I would stay away from any of the ports that are used by typical services. So again, don't use port 80. Don't use port 21. Don't use port 443 because that can actually cause issues within your network. You don't want to use anything that people know is a service. In fact, most of the time when I set a port, it's always 10,000 and above.
Okay.
I've got so much room. There's no reason for me to crowd the addresses that are going to be used on a regular basis.
That makes sense. And the danger of leaving this to just 80, like if you didn't assign it 999 and then push that to 80, like what if you just left it at 80? Then that means a lot of traffic from the internet would also go to it.
It just means that I don't want to make it easy for the attacker. It's not hard to figure out what it is.
Yeah.
But if I leave port 80 open on my network, people know it's a web server.
Low-hanging fruit.
Super low-hanging fruit. I mean, it doesn't really help if I make it port 10,000, but at least the super automated script kiddie tools won't think it's a web server until it pokes a little further.
Okay. Okay. I'm sorry. I'm thinking about the Xbox. You don't need to give it those. You don't need to assign like 999 and then go to port, the list of ports that you had. Like it's just you open those ports of that. And
no, you still would.
Would you?
Yeah. So for the Xbox, let me bring up my list here again. You would want to forward public port 88. To private port 88 on that IP address.
Okay.
You would want to forward public port 3074 to the private port 3074 on the internal. So
you wouldn't obfuscate those ports. You wouldn't do 999 send to 88 because that doesn't make sense.
But that's different because that Xbox it's communicating with a server that will only communicate on those ports.
Right.
Whereas me coming from the outside, I just remember if I want to get back to my network camera number 1, it's port 10,000, and camera number 2 is port 20,000, or so on and so forth.
Okay.
Right? So if I can set the communications, I'll go ahead and obfuscate the ports.
Yeah.
But if there's something on the outside that's communicating, I have to use the ports that it's using.
That makes sense.
Otherwise, it doesn't.
Right. It wouldn't work. It wouldn't work. Yeah.
It's just.
Okay.
I think we call it. That's no bueno.
No bueno. And I want my Xbox to work.
Maybe it shouldn't work so well.
Yeah, that's a good point.
By the way, for those folks out there who run Minecraft, that port is 25565. That's both TCP and UDP. So if you want to run yourself an internal server, you just use that. And by the way, I think I can obfuscate that. I can have people use user-definable ports in Minecraft. So I could set up multiple servers behind my firewall.
That makes sense.
Yeah.
Because you have the service, and then you can assign the outside port to go to the inside port. Okay. Yeah.
Ryan, I heard that you've got 99 problems.
But a switch ain't one.
No, it's not, because that's what we're going to be speaking about. It's all about switches. These are very, very much underloved pieces of gear in our network, because most of us, again, because we've come down to that part of the networking history where everything is contained within one box.
Yeah.
You've got the one box, that's your router, that's your firewall, that's your wireless AP, that's the switch. People tend not to think of the actual technology that goes into the network. And switches weren't always as simple as they are today.
Well, I wouldn't know because I wasn't around back then. No.
Okay, well, let me take you in the Wayback Machine. Hop on in. I'm going to bring you back to a time that was like way long time ago, back in the 1980s.
Like the dream sequence kind of transition. Yeah.
Yeah, but it used to be when I had a networking switch. It could mean many things. In fact, we didn't even really call it switches then. They were called repeaters. They were called hubs. In token ring, you had a ring. The whole idea was, how do I get one piece of equipment to talk to another piece of equipment?
Right.
It wasn't too long ago that we expected our machines to be standalone. In other words, my machine did what my machine did, and it could only do what it could do. Once we started realizing that by connecting machines to each other and having a bunch of clients, maybe a server, a mainframe, that suddenly I exponentially increase what my computer can do, well, it caught on, and that's what we have today. In fact, the entire mobile landscape, everything that we know about the internet today, from our mobile devices, our laptops, that's all based on networking.
Yeah, that's like that's the internet, right? Getting things to talk to each other and communicate and do so in a in a cohesive fashion. But also, I think my first experience with it wasn't a switch. I'm pretty sure it was a hub, which maybe we'll talk about the difference, I suppose. But was that I had a printer, I had my computer, and I had my Xbox all in my room. But I only had one Ethernet cable coming into my room, and I had to split that somehow. And that's where the hub or switch came into.
Right, exactly. And we're going to talk a little bit about that kind of gear. But first, let me explain that what we're using today, which is Ethernet, or a flavor of Ethernet. Ethernet, fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet.
Cat 5, Cat 6.
Well, see, Cat 5, Cat 6, that's the actual wire. So that's the specification of the wire that connects. Cat 5, Cat 6, actually Cat 3 back when I started, they could be used for multiple network topologies. But you had things like Ethernet alongside things like token ring. Token ring was an IBM thing, and it was actually a good idea. The idea was, when do computers speak when connected to a network? In the old star topology, what might happen is, you'd say you had 16 computers that were connected at the same time. They all wanted to speak at the same time, and you would get this cacophony, where if they spoke at the same time, they'd all have to retransmit. So they would back off for a random amount of time, and then try again.
Sounds like a traffic jam, but just like
that just keeps happening again and again and again. We would get these things called collisions, which were horrible because it meant that we had to keep retransmitting the same information over and over. Now, the theory was, well, if you have them back off, and it was literally, we call it the back off. If you had them back off for a random amount of time, the possibility that two computers would back off and then retransmit at the same time was actually very, very, very small. Problem is, once you start having 16, 32, 1,000 computers connected, that probability goes way up. And suddenly they're just always trying to talk at the same time. So IBM came up with this idea called token ring. Token ring was very simple. The computer with the token gets to speak.
The one token to rule them all.
The one token to rule them all. And it was literally connected. The network was a ring. It was a bunch of devices that were connected in a ring, and the token would pass from port to port to port to port to port. And when the computer had the token, that was its chance to talk.
That seems like it would be really slow, especially if you have like 1,000 computers connected.
Well, I mean, back then, like 4 megabit was fast, and that was a token ring. But, I mean, yes, it seemed slower, but the equipment was really expensive because it stopped collisions. There were no collisions in the token ring because computers only spoke when it was their turn to speak. So even though it seemed slow and very inefficient, the fact that you didn't have any of the retransmissions meant that in a larger network, it actually worked better.
Okay, all right. But then where did we go from token ring?
Well, we went from token ring, and by the way, I'm mentioning token ring. I could mention all the other protocols that we've had. Most of them have failed. Some of them have become sort of esoteric and used in data centers only. But we went with Ethernet because A, it was super, super cheap, and B, because it was super, super cheap.
Oh, okay.
We loved cheap. Cheap was good. It was actually a very low impact. You could make the equipment for far less than you could most of the other competing protocols and technologies. And the other big thing was, well, once we started having Ethernet and everyone started figuring out how to make it work efficiently, there was no real reason to invest in other technologies.
Okay. Well, like right now, I guess is Cat 6 kind of the standard at this point? Like
For premise wiring.
premise wiring.
So Cat 6 will get me 10 gig. I can do 10 gig over Cat 6. I can kind of do 10 gig over Cat 5, but for very short distances.
Okay.
But okay, as long as we're into Ethernet, let's talk a little bit about Ethernet. So when I'm talking about Ethernet, a lot of people, they like to use the term packet. Oh, I'm sending a lot of packets.
Right, or I'm dropping packets.
I'm dropping packets. That's not really how Ethernet works. Ethernet is a frame. The packets contained within the frame. All Ethernet is it's a post office. It's a way to say where every frame comes from and where it's going to. And in that frame, I can put anything, including TCP/IP.
Okay.
Okay, so it's a transport layer. That's all it is. Ethernet is just a way for me to talk from one computer to another computer.
That makes sense.
In the early days, we would have Ethernet hubs or Ethernet repeaters. Very simple devices. Essentially, I would have something that looks like this, and I'd have one computer connected to every single one of these ports, and everything that one computer says gets broadcasted out to all the other ports.
Right, okay.
Okay? Super inefficient. And again, I run into the collision problem, but it was cheap to make devices like that because all it had to do was receive information, send information, receive information, send information.
And when we talked about how to sniff or to monitor
tap,
networks, tap networks, yeah, that was kind of one of the things we talked about.
Super
because
easy.
hubs send out to everything, so
Yeah.
you can pick up data off of that.
No special requirements, no special equipment needed if you were using a hub because every frame of traffic went to every port. So as long as you were connected to a port, you would get all the traffic. The problem with that, as you might imagine, because we spoke about it at the beginning, when you have all the computers transmitting at the same time, trying to be heard at the same time, it's a cacophony. It's horrible. It gets very, very inefficient once you go above about 3 or 4 computers.
Okay.
So we came up with this idea of a switch. It's a switched network. In other words, clients only speak to what they want to speak to. They don't speak to everybody.
Right.
So if I have one computer that's talking to another computer, none of the other computers in the neighborhood should be able to hear that.
Right, and that's like what comes back to IP addresses, right? Like the sending straight to just that IP address.
Well,
like over the
yes,
switch?
if we were routing, because remember we talked about the difference between a
right.
switch and a router, let's talk about a bit more. So when we're talking about routing, we are talking about IP addresses. So it's from one IP address to another. But remember, I told you that when we're talking about Ethernet, we're not talking about packets, we're talking about frames.
Yeah.
So that it's not aware of the IP address. Your Ethernet
point.
switch, unless it's managed, has no idea what the IP address of your computer is. What it does know is the MAC address.
Okay.
Media access control. Every network device has a unique MAC address, which is a combination of letters and numbers. It's hexadecimal, so from 0 to 9, A, B, C, D, E, F, that it can use to create a unique identifier. Only that device has that combination of letters and numbers.
Okay.
And the switch, passing those frames, uses that unique identifier to know exactly where traffic needs to go in order for something to talk to something else.
Okay. All right, that makes sense.
Okay, now let's actually show you, because it's one thing
Yeah.
to say it makes sense. It's another thing to say, okay,
Let's see it in practice.
let's look at the nitty-gritty.
Or the
right?
diagram.
This is our beautiful network.
That's actually pretty good for you.
This is like Picasso
Yeah.
for me. It's like
You're
the
getting better
boxes
at
are kind of
this.
boxy and the circles are kind of circly. All right, so we've got our switch. This is switch 1. And off of switch 1, I've hung a bunch of different devices. So I'm assuming that this is like my biggest switch. It's my most powerful switch. I've got switch 2 and switch 3 that are plugged into ports on switch 1.
Right.
And then I've got computers. Anything that's a circle is a computer. So these are plugged straight into that switch. And then I've got an additional 4 computers, 2 off of each of the ancillary switches that connect into those switches, and those switches connect into this.
Okay, so you got switch on switch.
Switch on switch on switch.
Switch on switch on switch.
If, in the old way, I wanted to speak from computer, the one that has the MAC address ending in 11, and I wanted to speak to 17, the old way would be it would send a frame to the switch. The switch would send that frame to all the other ports. All those other switches would also repeat the same frame, and all of the computers on the network, except for the one that sent it, would receive that frame.
Okay.
That's super inefficient, right?
Yeah, it is.
Because it only needs to speak to 17.
But there's no way for it to know, I guess?
Now there is, by using that MAC address. So what it's going to do is, the very first time I turn on my network, so let's say it's completely cold, there's no power to it, I turn it on. There's a bit of memory inside each one of these switches that holds a MAC table. It's all of the devices that are connected to it, and it actually stores that unique address and associates it with a port.
Okay.
So what it's going to do is, the first time this network turns on, these computers, when they ask for their DHCP address, they're going to blast out their MAC address. That MAC address will be broadcast to everything else. So in this first instance, it does act like a hub. It acts like a repeater. So now the switch, let's say it's this one first, 11. 11 is going to send out its broadcast frame. This switch will say, okay, I understand that 11 is now on that port. It's going to associate that port with that MAC address ending in 11.
Okay.
It's then going to rebroadcast to these other switches, and these other switches are going to say, okay, 11 is now associated with this port. Does that make sense?
11 is now with that. Oh, okay, yeah.
Yeah, so that the instructions, the directions get passed down. So this switch knows that 11 is on this port.
Right.
This switch knows that 11 is on that port.
Okay.
So even though it doesn't know 11 is over here, it at
right
least
there.
knows how to get to 11.
The whole entity. Okay.
Precisely, okay?
Okay.
All right, so that's, in a nutshell, that's how it works. Now let's actually track some of this traffic.
Okay.
So 11, my switch now knows that 11 is connected to this port. This switch now knows that 11 is connected to that port. Let's say 11 wants to speak to 15. Now, I'm assuming that this switch, and when this client connected, it did the same thing that the main switch did, which is this switch now knows that 15 is connected to that port. Okay, and this switch knows that 15 is connected to this port.
And 14, right?
Well, not yet, because we're just talking about 15 and 11. So if 11 wants to talk to 15, what this is going to do is it's going to send a frame, and it's going to have the to address, and the to address is going to be the MAC address for 15. It's going to go into the switch, and the switch is going to say, oh, 15 is on this port. It's going to forward it to that port, and this switch is going to say, oh, 15, it's on that port, and it forwards it to the client.
Nice.
All right. So nice little direction. It's a little sequential map.
Yeah, that makes sense.
Okay. Over time, the MAC tables are going to fill up, and so they'll all start to recognize what's connected to every port. So this one knows that there's 12 on that port. This one knows that there's 13 on this port. This one knows that this one has 16 and 17 on this port. And this one knows that it has 15 and 14 on that port. So that table is going to fill up. So now I have a complete map to where everything is connected to. But remember, each switch really only needs a map of what it's connected to. This switch doesn't care at all that 17 goes to another switch. All it cares is that 17 is reachable through that port.
Right. Okay. And then once it sends the data to that other switch, that switch takes care of it.
Right.
Because it's that switch's problem at that point.
Right. And this is actually a little bit how routing works. But this is not dealing with IP addresses. This is dealing with MAC addresses.
Right. Right.
Okay.
Okay. And there's a little bit of memory there's memory on each of the switches that keeps track of all this.
There has to be, yes. And the larger switches, so the enterprise class switches, have larger tables. What you will run into every once in a while is you'll get a really, really cheap switch, and that really, really cheap switch can't keep up because it just doesn't have the memory to store all the devices that might be connected to it.
Okay. Is there a way to access the tables on a switch? Or is it like locked in?
If you have a managed switch, it's actually very simple. You go into the console and you can bring up a list of all the MAC addresses that are stored there. If it's one of these, like this is a dumb switch.
Yeah.
No.
No, it's just passed through.
I mean, unless you actually wanted to open it up and hook up like a logic probe. No. It's just this is a black box. Frames come in, frames go out. That's it.
Yeah, simple. Okay.
Super simple.
What if you put a switch into a switch like on your map over here though?
Oh, so okay.
I mean, you've got a switch into a switch, but what if you do switch 3 into switch 2?
Right. So that's actually a really good question because this used to happen all the time. I mean, we can keep it straight when it's on our blackboard. We've got 3 switches and a couple of devices.
Yeah.
But imagine you're wiring up a building. It would be really, really simple to accidentally patch one switch into another switch.
Definitely. Because you're just trying to extend it across the whole building.
Right. Well, in the old networks, this would actually destroy not destroy it, but it would take down the network. You're essentially creating a denial of service attack against your own network. Because what would happen is you would send a frame into this network, and it would have a multipath to get over to this other port. And so what would happen is you'd start to see the lines just blinking faster and faster and faster and faster, and then suddenly you're at this point where it just can't handle any more traffic.
Right.
Because all it's doing is broadcast packets.
Okay.
Today, we actually have a technology called spanning tree. And what spanning tree will do is it will recognize multipaths and it will kill one of them.
Okay. So then will it just not work?
Just won't. Oh, well, no, it will work. It's that port will be disabled.
Okay.
Spanning tree.
Spanning tree.
It's good for you. Trust the tree.
I had no idea.
Yeah. The other things to remember about this is, remember how we said that Ethernet deals with frames and not packets, right? And it's no IP address.
Yeah.
There actually is something in your computer that your computer uses that can help associate pieces of data with that frame that wouldn't normally be associated, like IP addresses. It's called ARP, Address Resolution Protocol.
Okay.
So, like, have you ever accessed a device on your computer?
Yes.
And you typed in the IP address, or you typed in like the name of the device?
Like typed in the IP address.
Yeah. Okay.
Yeah.
Well,
like Raspberry Pi.
In the Raspberry Pi, right? Or for example, when this computer is called Viper, and what I could do is I could put / Viper, and it will look through my network and find Viper and connect me to it, even though I don't have. Because I mean, how annoying would it have to be if I had to type in the MAC address for every computer I wanted to access?
Right, so you can give it a name. Okay.
Right, because remember, this is just MAC addresses.
Right.
ARP, Address Resolution Protocol, actually allows me to associate something with that particular MAC address. So for example, 192.168.1.17. ARP will say 1.17 is associated with the MAC address for this computer. So rather than having to remember the MAC address, I can just remember the IP or the computer name.
Right, which is much easier for humans to remember.
Yes.
Okay.
Yes. And actually, let me show you really quickly how that works. Let me jump out of this. Alex, I'm not sure if you've got my computer routed into the TriCaster.
I don't see it at all.
HDMI 1.
Oh, on one.
Yep. So what we're gonna, let me increase the size of my font here, because otherwise people are gonna go crazy.
Yeah, because in the past I have done networking where I type in the IP address for like a Raspberry Pi, but there are like computers on my network that are named that I've been able to access to.
So here's my my basic command shell, right?
Right.
So if I type ipconfig, it's going to give me the basic information for my my network, and you'll notice how this actually has an IPv6 and an IPv4 address because my computer is dual stacked. If I put ipconfig all, I get more information, like the DNS, the gateway, all the media specific information. Actually, hold on. My slash key is not working. There we go. Now I'm actually getting like MAC addresses, right? So see this? This is the physical address. This is that MAC address I was talking about. 5C514F 5C E298.
Right.
And the only reason why I'm okay giving that out is because I've currently spoofed mine, and this is not my real MAC address.
Okay.
But
well,
if I do this, first of all, I'm going to ping. Oh, wait, hold on. What's my IP address? I'm going to ping 10.135.249.255. 255 is the broadcast address. So all I'm doing right now, it's not going to respond. All I'm doing is I am hitting the switch, and I'm saying, hey, send this to everyone.
Okay.
And what's happening is those clients are saying, no, that's not me, that's not me, that's not me. But what that should do, unless Russell has configured this for security, which he might have, when I probably should have tested this beforehand. If I put ARP/A or -A, there we go. So this is telling me some of the other devices that are on my network. Okay. And actually, Russell did do his job. He locked it down. But like, if
Russell doesn't mess around.
This would be a really easy way for you to sort of probe. If you didn't want to run Nmap, you could just do this really quickly
To find out what devices are on the network?
Right. Like an unsecured hotel network, I do this all the time.
And so for MAC addresses, are they always... There's never a conflict of MAC addresses? Like, my laptop's never going to have the same MAC address?
Shouldn't be. There's a ridiculous amount of MAC addresses, and typically how they get used is manufacturers are giving a block. Which is why it's also easy. That's why I always spoof my addresses, because it's too easy to figure out what a device is by what its MAC address is, because it belongs to a certain block that was given out to Apple, or given out to Acer, or given out to HP.
Okay.
Now, I cause problems because I am spoofing an address, which means I might accidentally be stepping on someone else's address. But the chance that we will be on the same network passing frames with those MAC addresses at the same time, it's minuscule. It's
really low. Okay. Yeah. But so if you can spoof your MAC address, that doesn't actually change it. That like it's not a physical thing. It's all software, right?
It's all software. I mean, it does change. That's what's called the physical address. It does change it.
Yeah.
And it's super, super simple. The reason why we're not doing it in Networking 101, we might do it in Networking 102 because it is a useful tool. And actually, it's built into Windows now. You can tell Windows to spoof the address every time you log into a wireless access point, which is good because it means no one can use that to track your movement.
Right.
But I don't want anyone to do what happened the last time we talked about spoofing, which is someone spoofed the address on their cable modem, and then their ISP disconnected them because they no longer had a valid MAC address.
Oh, okay. And then can you not change it back?
You can change it back, but he didn't know what he did, and he was now knocked off the internet. So.
Oh no! And then he couldn't research to figure out what it was.
So So it's not like dangerous. You're not going to destroy anything, but if that happens, it's unfortunate, and people yell at me, and I don't like to be yelled at.
Okay, and so you did this search on our network, and it popped up with all these other devices, which I recognize the IP addresses, but then some of the MAC addresses are like FFFFFFF. Like,
right. You're always going to get a bunch of these. These aren't real.
Those aren't real.
Those aren't actually real.
So
okay. Don't worry about them.
Interesting.
Don't worry, Brian. It's okay.
I'm just curious. I was just wondering why there's MAC addresses that repeat themselves.
They're tired.
Because they're fake, I guess.
They're tired.
It was a lot of fun to do the Networking 101 and 102 series because it's something that I've been doing for a very long time and something that I hold dear. In this connected world, it helps if we actually understand the technologies that bring us together. Now, in just a bit, we're going to go ahead and jump into another segment of know-how videos, specifically security. I'm going to show you some of the things that you need to do to protect yourselves in an increasingly dangerous digital world. But before we do that, let's go ahead and take a moment to thank a sponsor of this episode of Know-How. Now, there are many ways to present your content on the internet. You could host a chat. Maybe you could put PowerPoint on the internet, give people PowerPoint poisoning. Maybe you just make a video that's really non-interactive that people can comment on and come back to time and time again. Now, those are all good. But if you want a really effective way to get your point across, if you want to reach out to potential leads, to potential customers, and to colleagues, then what you need is GoToWebinar. A GoToWebinar is the best way to host a webinar on the internet. They've hosted more than 2.7 million interactive web events with over 60 million views per year. GoToWebinar believes webinars are one of the best ways to interact with your prospects and customers instead of business presentations or company websites. Because with GoToWebinar, you can create custom email invitations, confirmations, and reminders. Or you can just let GoToWebinar handle it on its own with automated email templates. You can display your company logo and custom image in all webinar materials, which is important because you don't want it to be generic. You want it to have your look, your feel. You want it to have your branding. You spent time building up that brand. You don't want to throw it away just because you want to host a webinar. You can create and schedule pre-recorded webinars that are as interactive as live events, and it's mobile friendly. It lets you schedule a webinar, edit a session, or track performance from your iOS or Android device. You can also create up to 20 polls before the session or on the fly for audience interaction. You can add up to 20 questions to a survey and engage participants with Q&A. You can engage your audience with more than one presenter and a panelist. Up to 6 presenters can share their webcams and participate face-to-face. You can also broadcast a view of your desktop or a specific application. The bottom line is that GoToWebinar lets you be more involved with the people that you're trying to reach. And with GoToWebinar's reporting and analytics, you're just a click away from qualified leads, metrics, and data to improve webinars. You'll have end-to-end 128-bit AES encryption, and it's rated #1 in customer satisfaction. So here's what we want you to do. We want you to turn your next presentation into a conversation with GoToWebinar. For more information, visit gotowebinar.com/podcast. That's gotowebinar.com/podcast. And we thank GoToWebinar for their support of Know-How. Now let's get back to the action. throughout the year, there have been several security threats that have popped up, but no more than WannaCry. WannaCry really caught the imagination of the security folk because it was something that spread easily and had a serious impact. These are two segments that look over WannaCry and perhaps a way to protect yourself when you're out in public.
Okay, this is a Windows 7 computer, so I'm going to go ahead and come in. This is a fresh installation, which, by the way, was difficult because whenever I'm doing this kind of work, and by the way, I'm not a security researcher, I'm not an expert in this, I just know how to play with it.
Yeah.
I don't like using VMs because there are too many malware packages now that can be VM aware. They know
They're
if
in a
they're a
VM.
VM and they don't exhibit regular behavior. They kind
really?
of hide from you.
Ah, okay.
But this is actual hardware. What I've done is I've actually just made a lot of clones. So, Kara, if you go to the overhead, this is just an old ATX motherboard. I've got an SSD, but I've also got a stack of SSDs, and these are all clones of the same operating system. So I'm going to infect these, and then I'll just swap them out, and I get a brand new, fresh one.
Okay.
But the nice thing about using this kind of a setup is I know that this is going to mirror real world.
And
Because-
it's contained, right?
Yeah,
we
this
don't
thing
have
is-
this hooked up to anything else.
Well, it is, but
not on our network.
no.
No, not on the Twit network.
No, just it's its own private little network.
Yeah.
All right. So go ahead and go back to my computer. There we go. So I've got a couple of things on here. This is the payload. So thanks to Lost, by the way. Lost Boy, he's the guy who makes the badges for DEF CON. Fantastic guy. He helped me track this down. This is not the original variant.
Didn't he send it to you in this?
Yeah,
This
this
little
is-
package? It says,
Really don't
warning
open
may contain dormant cyber pathogens.
Yeah, just
It's serious.
this is not a joke. That's serious. Don't mess with that. But if you go back, so this is not the original variant. This is one of the ones that's been slightly modified. This actually doesn't have the kill code in it. So the kill code was discovered by accident by a British researcher, and he found out that when you started up the software, it beaconed out to a website that didn't exist. And so he registered the domain, and once he did, and that beacon started getting a response.
Yeah.
Which it was a TCP session, so it was a not just UDP, it was a connection. It would not run. So it was a kill switch website.
Right,
And
but
people thought, oh, it's solved, but then they just made new variants that didn't have that.
Didn't have, yeah. Oh.
Yeah, and actually this variant doesn't have it. So this does not have a kill switch.
It makes it sound so
It's better,
dangerous.
right?
Yeah,
Yeah.
it's totally better.
Okay, so go ahead and go back to this. Since this is a clean computer, I put a couple of files in here. So these are just text files from old know-how projects. They're all readable right now, which is what we like. That's how it should be.
That might change.
That might change. So this is the payload. There's many different ways that you can get this payload. The first is something that we already mentioned, which is if your computer is vulnerable to Samba 1.1, which this is. This is Windows 7 from 2015, so it has not been patched. You can just be infected over through the Samba protocol. It does a remote execution, and now you're infected. You could also receive this as an attachment, and if you run the attachment, you're going to get infected. Or you could say get like a PDF file that's running something off of a server for remote code execution.
Right.
You can also get infected. So there are many different ways to get infected. Essentially, right now, this is going to act like any crypto ransomware.
So you could go to a URL that then initiates the script and then just runs this?
Yep.
Yeah.
Yep. It's worse on XP. 7 is at least a tiny bit protected. Oh, by the way,
10.
We'll talk about this later, but people have asked, well, will this affect you if you're not running as administrator? Yes, 100%. It will. So that's not going to protect you. But this is something you should not do. Let's go ahead and run it.
So imagine, we
Okay,
went to a
so
website.
automatically you see a few things have happened here. Let me start with the task manager.
It dropped some files on the
Yeah,
desktop.
there's a bunch of files on the desktop, and if I go to my processes, there's one here now that's using up 25% of my CPU. That's one of the first warnings, but of course, if you see that, it's already probably too late, because what it's doing right now, it's going through all the files it can find on this computer, and it's encrypting them. And this is how fast it is. Let's go back to our sample data. Look, oh no.
So, oh wow.
See? So what it's done is I'm actually capturing it in the middle. This is the encrypted version. The original version is still there. So it's still going through all the files on my computer, and as soon as it's got them encrypted, it's going to delete all the originals.
And the encryption itself isn't like a nefarious thing because you can download encryption programs to encrypt your stuff, but you're the one that owns the key.
Yeah, they're going to own the key. Now, see, this is what happens. Like, for example, even if I change this back to doc, let's do this. Yes. If I try to open it up, see, now it deleted all the original files. See that?
Oh.
They're all gone now. So and this is all happening in the background.
Oh, that's messed up.
And so now if I try to open it, look what it looks like.
It doesn't recognize the file? Or
no.
It's trying...
Well, actually, hold on, let me change
Oh, I see.
X. Let me change the name.
It was trying to find, the file.
Yeah, there we go. Oh, I'm trying to type
types today.
I'm trying to type on a monitor that's far, far away from me.
I keep walking up to the screen, yeah.
Let's make it bigger.
Make it bigger.
There we go. Okay, so if I open this up,
We can see it better too.
there we go. It's
So it opens up the dock, but it's
but
gobbledygook.
look what's at the very top.
Oh, so it puts the WannaCry header on there?
Which is what we call it. So yeah, this is an encrypted file, so I cannot read this. Now, if I'm going to let this sit for a while because it's still priming, it's still going through its thing, and something's going to happen in just a bit, and it's what most people will see the first time they've experienced WannaCry. But Kara, come back to us while we wait for this. It's going to take a while. I mentioned elegant attacks,
right?
And an elegant attack would not be this; would be something like the Stuxnet virus, which allegedly was developed by probably the United States. It was
maybe collaboration.
Probably in collaboration with Israel. But it was a virus like this. It started off as a Trojan that also had a worm payload. And that was elegant because it was looking for a very specific target. What it was looking for were centrifuges.
Right.
Specifically,
nuclear.
The types of centrifuges that are used to separate nuclear masses.
Right.
And what it would do is, if it did not detect a centrifuge, it put all the attention on spreading. It would spread to any USB drive, any network connection that it could. Once it found the machines that it was looking for, it would oscillate the operating frequency. So the centrifuges would speed up, slow down, speed up, slow down. Essentially, they tore themselves apart.
Wow.
And we know it was probably a nation-state attack because if you look at it, it was a virus, a worm, a payload, specifically designed to take out nuclear enrichment.
Right.
So that's not a for lulz attack. That's something that someone had a target in mind.
That's not a script kiddie. That's not even like a criminal organization.
Here we go. Okay, if you go back. So this is the screen. Oh,
what happened to my computer?
Yeah,
Can I recover my files?
This is going to tell me. So look, it's got the date, and it says, hey, you know what? You've got 3 days. So you now have 2 days, 23 hours, 59 minutes, and 44 seconds to pay us $600 in Bitcoin. Actually, this one's 300. Yay.
300?
Yep.
And what's a Bitcoin going for these days? Isn't a Bitcoin like $1,000?
Yeah, that's not bad.
Jeez.
Now, you can decrypt. It will give you a taste. So if you hit decrypt, it will let you decrypt some of your files, but it's basically just tease you saying, oh no, see, I can bring them back. Now, you want the rest of them?
Man, that is really, that's devastating if you see that.
Oh, by the way, look at this.
What's that? What's going on here?
It's Windows security saying, hey, I think something's happening.
Wow. Yeah, something did happen.
Here's the thing. Windows is still operating. Windows still works. So it didn't destroy the operating system. It selectively went through and found all the data files. And on this particular case, this is the only data files. And if you go here, if you open the README, they tell you what they've done.
Wow.
And the scary part about this is if you look through the files that it dropped here, it's got complete loadouts for all the languages of the world.
Oh, wow.
So they intended this to hit as much of a target surface as possible.
And there's nothing you can do other than pay them and then decrypt your stuff? And
yeah, it's very, I mean, people think they're going to brute force the crypto. I've never heard of a successful case of doing that. I'm sure there is, but I haven't heard of it.
Well, then, I mean, what guarantee do you have even if you pay that they'll give you the key?
Well, that's the business model. I mean, if word gets out that they're not giving your files back, then no one will pay. Yeah.
I did read an article, too, where people were, they weren't able to pay because it's so complicated for people to know what a Bitcoin is or even, use a Bitcoin. so that like a lot of places they're like, we don't know how to pay with the Bitcoin, so it's just that stuff is gone.
Womp womp. That's kind of sad, right?
It makes me want to cry.
Well, it all makes you want to cry. All right, so the way that I deal with this is I now consider this an infected drive, which is...
So if you were to
motto.
plug that into, well, not another computer, but onto our network
Actually,
here, would that start?
Very good point. I'm going to switch inputs here really quickly, Kara. You're going to get my computer, because I want to show you what happens if you plug this into a Windows 10 machine. Again, folks, do not do this at home. We're doing it so you don't have to.
This is getting me a little worried.
It could get me a little fired.
Don't worry, we're not trained professionals.
We are not trained professionals. We have no idea what we're doing.
Don't do this at home.
So I've got a little USB enclosure. Kara, do you see my computer on HDMI 1?
Yeah.
Okay, if you could go ahead and bring that up. Now, this is my personal laptop. It's running Windows 10. So look what happens when I plug this in.
I'm hoping it says, no, go away, bad.
See at the bottom? Threats found.
Windows Defender.
So Windows Defender is not letting anything on that run, which I like that.
That's good.
But this is how I made my my clone. So I'm just using a Cronus, their true image. And what I have is I already have another SSD plugged into this with a clean version of that Windows 7.
Right.
And I'm just going to copy it back over.
Okay.
So as we're working, it's just going to go ahead and redo it. It's going to wipe out everything on that drive.
Starting fresh again.
Start nice and fresh. Now, I could do this with VMs, but again, I'm kind of a junkie on using this method because it gives me the purest results.
Yeah.
I don't have any VM getting in the way. There's no chance that the malware is going to detect that it's in a virtualized machine and decide not to release its payload.
Is there any way that it could get out of a VM? Nah.
I mean, yes, we've proven there's definitely
Is
a
it
proof of
like that
concept.
hypervisor or something can get
Yeah,
compromised?
there's a couple of ways to do it. All right, so it's gonna do that. What I'm gonna do is I'm gonna go ahead, Kara, if you could come back out to us. I'm gonna switch back to the other machine, and I'm gonna go ahead and install one of the other drives, so that we can get back to business. Now,
so this would work even if you had a Windows 10 install, right? But not one that's like patched within this week.
The crypto ransom will work.
Yeah.
But the SMB vulnerability does not exist on Windows 10 anymore.
Okay.
So you could infect a single machine. You cannot infect a bunch of Windows 10 machines over the network. That part is gone. Which is why this hit mostly Windows XP installations, because Windows XP installations weren't being updated. Even Windows 7, I had to go back into my archives to find a version of Windows 7 that was still vulnerable to this, because everything I have has been patched.
Okay.
Aside from the tapping computer.
So your
we'll get back to
average computer user who has been keeping their stuff up to date should relatively
if
be
they've
okay?
got Windows 10, yes. And if they've got Windows 7 and they've been keeping it up to date, yes, they should be fine. Should.
Of course.
Just don't run it.
Now that I think about it, I'm like, there is one computer on my network that's still running Windows 7, and I don't think it's updated because I never use it.
And remember,
I
all it takes is one machine on a network, because once you have one infected machine on a network, that machine will search the entire network for all the vulnerable machines. If it finds one, that machine is now infected.
I might have to remote into my router for a second.
Okay, Brian, let's go ahead and get back to business. We've got our Windows 7 box back up and running. Kara, if you please go back over to HDMI 1. Let me log in with our cute little dog there. Actually,
Oh, a little
I think I
Doge.
just typed in the wrong password. Oh, no, right
No,
one.
you're good.
Yay! Okay, so on this one, I already have the pathogen is loaded, but I want to go ahead and put the data files there. We're going to give it something to encrypt.
Do you want to restart now, or do you want to restart later?
You know, I don't ever want to restart, Brian. We'll restart later. Let me copy this over first. That's the one thing with the cloning. Every time you get a fresh installation, you have to restart. Something to remember about this, by the way, is you have to pull the drive out of the computer before you run the payload, because otherwise it will also encrypt the flash drive.
Oh, Smart. I wouldn't have thought of that. I probably would have made that mistake. Did you?
No, because there's.
You were aware of it.
I actually have protocols for this. I've been kind of rusty. I haven't done this in a while, but when I'm doing security stuff, I have a clean side and a dirty side, and you can go from the clean side to the dirty side, but you can never go from the dirty side to the clean side. And that's just how I protect everything.
It's like a medical procedure.
It really is, because I mean, you got to remember, I'm working on Windows machines. That's my thing. So I'm working on Windows machines with a pathogen that can destroy Windows machines. That's yeah. I actually have a Raspberry Pi and a Mac that I keep there just because I want something that I can safely work on these files with. Like if I have to get into it, I'm afraid of accidentally executing.
To dig through it. Yeah, because you keep mentioning that it's not really an elegant file. Is there anything that like stood out to you that made it that way?
Yeah, like if you actually look at the source code, so people have decompiled this. It looks like people just got packages, slammed them together.
So this is basically just the stuff that got pulled from the shadow brokers. They got the information from the NSA, and then somebody just threw like stuff on top of it.
Yeah.
Okay.
Yeah. Woohoo.
So, and this is stuff that wasn't patched because the NSA was stockpiling a lot of these exploits too.
Yeah, Microsoft did a big thing about saying, look, this could have been avoided if the NSA had told us about this exploit. We could have patched it a long time ago.
Yeah.
But of course, the NSA didn't want that.
Because they want to use it. Yeah.
So, yeah. How about that? All right, let's go ahead and do this again. We've got my. If you go over to HDMI 2, Kara, we're going to go ahead and start up a new. There we go. So this is tapped. So right now, Kara, if you go to the overhead, this computer is attached to this tap, which is going to a router that goes nowhere. So this doesn't actually have internet access, because I also don't want this sending probes on the internet. That's just mean. Yeah, that's a bad thing. But this is another one of the things, like a bit of my protocols. Whenever I'm running anything that's network aware, I have the infected color and the clean color. So infected here is purple. The infected never goes into a machine that's not supposed to be deliberately infected.
Okay.
Whereas this is just a tap line. So this does go to a Windows 7 box.
But you're just reading what's passing. You're not sending anything.
This is not actually connecting. You cannot communicate to the orange wire through the purple wires.
That's smart.
Yeah, so that's how this is going to work. So I'm tapping it. Now, Kara, if you go back to HDMI 2, this is what it's reading right now. So this is pretty typical for a Windows 7 box. I've got a bunch of DNS queries for Microsoft.com. It's actually trying to talk to the update server. I've got a couple of ARPs, and that's address resolution protocol. So it's just saying, okay, hey, I'm new here. What's on the network? But not a whole lot. It's actually kind of quiet. This is all just pretty typical traffic. In fact, let me go ahead and switch this so that it doesn't auto scroll, because I want it to stay with the most. There we go. There we go. Okay, now we got to do the thing, Brian. Actually, here, why don't you do the thing?
You want me to click the button?
Yeah. So. Go back to the other computer, Kara.
I'll do the honors, the breaking champagne over it. And so, I mean,
actually, open up the sample data so we can make sure that those are still. There we go. And actually, let's go ahead and open up hold on, a task manager window so you can see the process as it first starts up. There we go. Oh, stop that.
And so, I mean, no one in their right mind would have downloaded this to their desktop.
You really should.
And then activated
that'd be bad.
But
okay,
imagine I went to a website.
And so now we can see how much CPU time it's going to take up and how quickly those files get encrypted. So the process has started. 2, 3. Oh, so it's like 4 seconds and the files have encrypted. However, it's still going to be a couple of seconds. You're going to get a minute here before it deletes the unencrypted files.
Because is it still probably probing?
It's probing. It's going through everything. So it's anything that's attached, anything that it can reach over the network, anything that might be hooked in over a USB port, it's going to encrypt. And once it has them all cataloged, it's going to start destroying all the unencrypted files.
Is it sending any traffic through the tap now?
Well, yeah, let's take a look. So go ahead and go back to the other computer. It's now become crazy busy. So if this was the first variant, one of the DNS entries that I would see here would be sending it to the kill site. But you'll notice there's a lot of traffic that's been picking up. One of the The most obvious ones is LLMNR. So let me separate that out. LLMNR. What this is doing, this is the local link multicast name resolution protocol. This allows the computer to find out what else is on the network.
Oof.
So all it's doing right now is it keeps reaching out into the network saying, hey, who's here?
Anyone
Hey, I'm
here?
new in the neighborhood.
Are you vulnerable? Oh, let me come over.
Now, if there was another machine, what you would start to see is you would start to see a lot of TCP port 445 traffic. That's
Back and
Samba.
forth. Right.
And what that is once it knows the other machines on the network, it will start probing. It will say, hey,
Right.
are you vulnerable to this? Are you vulnerable to this?
Which on your inside your house network, that port would be typically open, right?
Inside.
Yeah, inside.
If it's open outside, then
well, you're getting hosed.
Yeah, you're getting hosed. That's a really, really bad thing. But so this is actually one of the signs that I now have my network program to look for. LLMNR isn't used that often. So if suddenly I have a computer that is just spewing those packets, it just keeps asking who's here, who's here, who's here.
Yeah.
It's probably malicious. And so my network, my switch, has policy on it. It will automatically disconnect that port. It will put it on its own VLAN.
Oh, okay.
So it still thinks it's connected, but it can't touch it. It'll warn me. It'll say, hey, I'm noticing suspicious traffic. Do you want to allow this to go through?
Okay.
Right.
What is it? Somebody in the chat room just asked a good question. What happens? Oh, it was Ed. What happens if you get infected? It's encrypted all your files, and then you make like a new file. Does it encrypt that after?
Yep. So
after the fact?
Anything I plug into this computer now
We'll get infected.
will get encrypted. Because it's running. That's always going to be running.
Oh boy.
It's now a process that's running in the background. And even when I kill it, remember the double pulsar backdoor is still there.
Yeah. Oh man. So if you plugged in an external drive into this after it's been infected,
it would encrypt the
it would
external
encrypt
drive.
that. But it wouldn't then, you wouldn't then be able to take that drive and plug it into another computer. It wouldn't then activate the exploit.
No.
It would just be that drive
Right.
encrypted.
So it'd be all the data on that drive would be encrypted, but the exploit is actually not carried in a USB connected device.
And
Now, if for some reason it was this drive, which actually does have the file on it, and I had like an old XP machine that did auto run, okay.
yeah, then it would. Yeah, then it would.
But that's such a confluence of really, really bad things.
Yeah, I don't see
there we
that.
go.
Oh,
So it's
and-
officially, there we go.
Oops.
So now it's switched over, and I should get my little, there we go.
And the timer has
Now,
started.
okay, go ahead and come back. Notice to the other computer.
Mm-hmm.
See all this?
Yeah.
So now that it's firmly entrenched, these are those TCP packets that are reaching out looking for the kill switch.
Okay. Which other versions or more modified versions don't do now.
Right. But all so let's port 445 is actually in use now. Look at all this traffic that this machine is generating. There's nothing else on this network. It's just this infected Windows 7 box. And what it's trying to do is it's trying to propagate. And you'll also notice there are some links here. There are some addresses that don't exist in the network. They're outside. So this is actively trying to get out into the internet to try to infect machines out there.
Jeez. Wow. So what happens if you? So it says Bitcoin. When you what happens when you click that? That just takes you to a Bitcoin site.
Well, no, it's if you go back to HDMI 2 or HDMI 1. I'm sorry.
Because there's no way. I guess that's kind of the nice thing about the Bitcoin is the anonymity.
Yeah.
But
Well,
like finding out where the Bitcoins are going
this
to or who
actually,
you're paying.
this does have instructions. So if you want to pay, they give you instructions on how to get there. Because they want to make it as easy as possible for you to do this. By the way, look, here's the language loadout.
Right.
So they really wanted this to be an inclusive package.
Is there any? Has anyone reported like how much money they've probably made from
Probably
this?
about 70,000 so far, which for something of this scale is nothing. And again, it really isn't elegant.
No.
It works. It's very effective because it's using something that the NSA developed. But I mean, it's basically just crypto ransomware that they've tacked a worm onto.
Right.
Yeah.
Piggybacking.
Yeah. All right. So now we see what's happening. And I love this. If you could, can you put this in a small screen, the little Wireshark,
What?
So HDMI 1, put it in a 2-box. I want to see it keep running because it's so much fun. Oh, the other input. It's so much fun to see what this is trying to do. Because if you watch it long enough, you'll see it keeps hammering this network. In fact, if I brought 2 laptops with me, one of them is a completely vulnerable Vista machine. And I haven't done this test yet, and I don't want to do it live, but I want to plug it into this network
and see it propagate to
see how
another
fast
machine.
it gets over, because I know that's vulnerable to SMB.
Yeah.
I also have a Windows 10 laptop that I know isn't. But this acts differently once it knows there's other devices on the network. Once it knows that there's at least one other device, that traffic screen just goes crazy, because it just starts throwing traffic against the other device. So that's one of the things to look for. Look for LLMNR, that's a dead giveaway. Look for a lot of traffic on port 445, that's the Samba port, even if you're not transferring anything. And then also look for a lot of probing attacks outside the network. And of course, the only way you're really going to see that is if you have a tool like a tap that lets you intercept this traffic.
Yeah, and as scary as it is with just the ransomware, I guess with this attack, you could piggyback anything you wanted onto those.
Absolutely.
So you could do it more subtly. Like you can infect computers without anybody knowing, or leaving like traces that are as obvious as encrypting all the files. Like install keyloggers or, well,
crazy. I mean, that's the thing. There are frameworks like the Metasploit framework, which is great. It's a research framework to help you learn about how these things work, just like what we're doing right now. But it essentially allows people to say, I'm going to take something from column A, something from column B, I'm going to put them together, and now that's my attack package.
Wow.
It's really simple to do. It's actually kind of scary simple to do.
I'd like to talk to Mudge about it.
Yeah, right?
Yeah.
Good. All right, so I'm going to go ahead and, I just kind of...
You like watching the traffic go by?
I'm sorry.
It's fun because it's safe now.
It's safe,
yeah.
right. If this was loose on my network, I would be freaking out right now.
Right.
Let's
You'd
go
be
ahead.
unplugging wires, turning off all the power. Yeah.
Let's go ahead and talk about some of the practical things that you can do if you're worried about this. The first, I'd say, of course, it's always going to be personal security. You don't open attachments. You don't even accept email from people that you don't know. I know that's very difficult for a lot of people, but especially if you're running something like an old email client that auto previews files, that could be really, really bad. Make sure everything is patched, everything is updated. If you're using Windows XP or Server 2003, stop it. I know there's a lot of infrastructure that's tied to those older versions of Windows, but this is just going to get worse. This is patched right now, but this is not the end of it, because the attackers know that there's such a large installed base of machines that will never be updated that they're always going to attack this vector first. It's the lowest hanging fruit.
Right.
Something else is backup. I know this sounds very simple, but yeah, you need backups. You need lots of backups, consistent backups. And here's the thing, you need to back it up and then remove it. It's got to be
air
disconnected.
gap it or something.
Yeah, like if you were backing up to a NAS that was mapped to your computer, it jumps. So it's not that the cryptoware runs on the NAS. It runs on the computer, but it will encrypt everything on the NAS and then delete.
Which could be terabytes.
Could be terabytes.
Yeah.
Right.
Whew.
Yeah. That one will take a little bit longer. So you saw how long it took on a machine that had almost nothing.
Right.
As you increase the amount of data that it's encrypting, it's going to take longer and longer and longer.
So say that you think that you've been infected and you do have like a machine with a larger amount of files that need to be encrypted, and you're like, why is my machine running slow all of a sudden? Could you look through your task manager for that and then be like, okay, like shut down the computer?
Shut it down, pull the drive out, plug it into another computer, copy off the files.
Okay.
Because notice how it didn't give us the warning screen. If you go back to HDMI 1, Kara, it didn't give us this warning screen until all the files were deleted.
It was completed.
And it knew that it had done everything it could. So there is a response time here. And if it's encrypting a lot, there's a chance that you can get to it before it's finished encrypting, and then maybe it hasn't yet deleted the non-encrypted files.
Okay. Whew.
you'd be really lucky. So don't count on that, but it's
No.
possible. If you see that file pop up in your task manager, yeah, shut it down immediately because you're in the process of encrypting. Because I know all of my traffic is going through this Raspberry Pi, I can hook up a tap. We've talked about this before. I can hook up a tap and I can see exactly what kind of information can be seen by my ISP. So my ISP owns the line. They own the
Right.
wire. Let's simulate what the ISP can actually deduce from my traffic.
Oh, okay, yeah, that's smart.
All right,
I like
so
that idea.
you may remember this. This was the Shark Tap that we had a while back. Actually, Alex, I think we have a link for this. It's it's a little pricey. It's about $180, but the nice thing about this is it's a super simple tap that will allow me to go inline on any gigabit network and receive all the traffic that network might be transmitting or receiving.
Right.
So here's how it's going to work.
Okay.
I've got this black line going into the Raspberry Pi right now. I'm going to remove this, like so. So this is this right here. This is the line that's going to the internet.
Right.
I'm going to plug this in on one side of the tap, like so, and then the other side is going to go into the Raspberry Pi, like this.
So if you were hooking this up in your home network or something, the black one would be going to what, say like your Synology router or something?
Correct. Right.
And then to the Raspberry Pi, and then the orange one going to another computer so that you can now see the traffic.
Precisely. So this orange cable that you see is actually going to this laptop that's on my desk right here. Alex, if you switch over to HDMI 1. So this is running Wireshark. All this is going to allow me to do is it's going to allow me to use the network interface, the Ethernet interface, plugged in via USB, which I believe is number 4, and I can see exactly what kind of traffic is passing. So this is only for my phone. My phone is the only thing that's connected to this thing right now. So for example, if you come back to the overhead, let's actually click on one of these stories. So we click on this one. All of the traffic right now is passing through the Raspberry Pi access point, through the tap to my Wireshark. So if I go over to the Wireshark, for example, I can type in DNS to filter as I'm scanning for just DNS entries. Anytime I search for a new page or click a new link, you see all those DNS entries?
Yeah.
That's the unencrypted clear text that my ISP can see. And I'm only looking at one particular protocol. I'm only looking at DNS because it actually is quite important. Because if I click down on these individual entries, you can see exactly which website I'm going to.
So that would point to, or it does say on the
Oh yeah,
right,
yeah.
doesn't
Just
it?
like this one, this is an Amazon link. There's a Wall Street Journal link here. If you read down below, actually go even further down, Alex. If you read down below, even further down. There you go. See down below here, you actually this is doing the hexadecimal translation, and it will actually show you which site you just requested.
Wow.
Okay, and it'll do that for all of the different entries. All of these different entries, like this is going to double click. It shows you how many different things you're actually accessing anytime you access a page. So I may be accessing Reuters, but like this one's going off to Cloudflare, this one's going off to Amazon, this one's going off to Microsoft.
Right.
These are all the different sites that now have a little bit of the page that I'm being served.
Right.
Okay? I don't want that. I mean, yeah, this isn't bad. This is not horrific, but I don't want people to have that information.
Right. This is par for the course when going on the internet.
Precisely. All right. So here's what we're going to do. Now that we have this access point on our Raspberry Pi, we're going to install Tor underneath it.
Right.
We know all the mechanics are working. I'm able to go from my phone to my Wi-Fi access point on the Raspberry Pi and the Raspberry Pi out into my Ethernet network, which gets me onto the internet. So I know that works. All I need to do now is tell the Raspberry Pi how to take the traffic it's receiving, put it into Tor, and send it out into the Tor network.
Right. And then that's what will basically not allow ISP to know what you're searching for, I guess?
Kind of. So here's how the Tor network works. I am still going through the ISP, but it's an encrypted tunnel.
And
So
it's bouncing off a bunch of other
It's bouncing off of
nodes on
other
the Tor
Tors. So
network.
the very last node, that if you could find the exit node on the Tor network that I'm going out through,
Right.
then you could do some damage. Then you can work backwards and not completely easily, but better figure out who's coming from where. But if you're just an ISP looking at the traffic, it looks like garbage. There's nothing. You can't even read my DNS entries, or at least you shouldn't be able to. We're going to get that in just a little bit. So let's go ahead and go back into my terminal window. We're going to get fast and furious with our commands here, so I'm definitely going to need my little text file. So let's open up a terminal window. Now, the first thing we're going to want to do is we need to update our installation because this is actually not the most recent distribution of Raspberry Pi. And also, I just added a script that was created a while back. That's added a bunch of dependencies that I might need to fix. So this is really simple. Sudo apt get update. Apt get is just, it's a command that allows me to check all the packages and all the dependencies that are currently inside of my Raspberry Pi Raspbian installation. And if any of them are broken, it will fix them. And if anything needs updating, it's going to go out and get the most updated package and install it.
Right.
This is Windows Update, except not as stupid.
It's not going to force you to another version
in the
of
middle
the
of an
OS.
episode.
Yeah, in the middle of the episode. And if you've ever done like a Raspberry Pi project, that's like one of the very first things that you ever do.
It's not like going to say, hey, I noticed you're in the middle of a show. Would you like me to upgrade you to a new OS that's going to take 10 hours to do?
No.
Raspberry Pi won't do that.
The nice thing about being able to type it into the terminal too is it gives you the power.
Yeah.
Not Microsoft bugging you about it.
I'm all about the power. All right, so I'm updated. If you go back to my terminal window, apt-get has done its thing. Now I'm going to need to go ahead and do a little something to install Tor. Super simple. Sudo apt-get. Oh, actually, I should probably be in the right window here. Sudo apt-get. This is super complicated.
Right.
Install Tor. I know, right? Go figure. So what it's going to do right now, it's reaching out. It's going to install all of the packages and dependencies that are needed for Tor.
Would you like to continue?
Yeah, this is going to take a while. Now, as this is working, let's talk a little bit about what this is actually going to do, Brian.
Okay.
So when this receives a packet over the Wi-Fi interface,
So from your phone to...
from my phone or a laptop, any
whatever,
computer that's
whatever's
using the
connected.
Raspberry Pi as an access point, it's going to take it and it's going to encapsulate it in the first layer of encryption. It's going to send it out into the Tor network, and then it goes to another node, and it's going to add another layer of encryption. And every node it hits, it's going to add another layer of encryption. This is why it's called the onion router. It's got layers. So even if
like an ogre.
like an ogre,
Or a parfait.
So even if you can see the layer in front of you and the layer behind you, you still probably don't know where it actually came from. That's the whole idea.
How does it know where it's going then?
Well, because you know where it came from and you know where it's going, but you don't know 2 steps back and you don't know 2 steps forward.
Oh, that's interesting.
Right? That's how it's supposed to work.
Wow. Okay.
Okay. So if you go back to my terminal window, this is all good. So Tor has been installed, but it is not configured yet. So here's what I have to do. I have to go sudo nano, and nano is just the text editor, /etc/tor/torrc. And it will get me into here. Now, this is where I would definitely say, please just copy over from the text blob that I give you because it's complicated to do it any other way. If you go out a little bit, Alex, you're going to see this. I have this in the log file. It says add the following to the config file. So just copy and paste this entire blob from log notice file all the way down to DNS list. All this is these are all of the environmental variables that I want in there.
Right, that you've customized for your network, it looks like?
Precisely. Okay, and if you go back over to the text window here, I'm just putting it between these 2 sections of comments. I'm just going to paste it.
And if you've ever followed any of our programming lessons, you'll notice that the hashtag that like makes
comment.
That's
right.
commented out. Yeah.
So what I've done is I've added these lines right here, and this is just telling it like I'm going to be using port 9040. That's how it's going to get out and into from the Tor router. I'm giving it my listen address at 192.168.42.1, and I'm giving the DNS listen address at 192.168.42.1.
Okay.
So I'm going to save this with Control X and save the file.
Enter.
Good. Back out here.
Boom.
Okay. This is not done because what's happening is Tor is set up, but the IP table, and IP tables is a function inside of Linux that allows me to configure traffic rules, packet rules, what happens to a packet. It's kind of like the firewall.
Okay.
That's still using the old set of rules, which was just a straight AP. I need to dump those rules, and then I'm going to put in new rules that forward all the traffic through the Tor service.
Okay, that makes sense.
Right. So if you go back to my my terminal window, I'm going to put sudo IP tables dash capital F. That just dumped one set. Now sudo IP tables dash dash T nat, and dumping the nat rules, There we go. So I've dumped all the old rules. So now I can create new rules to route the traffic through Tor. And again, I'm going to go back over to my handy dandy text file here so you don't have to type the entire thing. The first thing I want to do is I want to route DNS. So all my DNS entries, rather than going in clear text, are now going to follow this. Paste it in, please. You'll notice it's sudo IP tables -t nat -a pre-routing -i WLAN 0 -p UDP. So we're doing UDP packets here. -- dport 53 -j redirect -- ports 53.
Okay.
Okay, so this is going to redirect all of my DNS routing through the Tor network.
Oh, okay.
Okay, the second one that I'm going to want to do is, now that I've redirected DNS, I need to redirect TCP, which is the protocol that I'm going to be using most of the time. Okay, Control C.
Okay.
And this looks just like the other one. This is just a rule set that's going to route all my TCP traffic through port 9040.
Right.
Okay, so run that.
Now, are you setting it to 9040, or is that like the default Tor?
That's
stuff?
that's Tor.
Okay.
Yeah, it's got to be 9040.
Okay.
All right. Now, just to make sure I didn't mess anything up, let's go ahead and check my table. So I'm going to put sudo IP tables up. No, actually UP tables. That's much better. Dash. What is my command? -t nat capital L. Okay, good. So I've got a redirect on UDP and I've got a redirect on TCP. So I'm good.
Okay.
My rules are great.
If you hadn't done it right, what would you see? Would it just say?
You actually you might not even see the entries.
Yeah. Okay.
Just make sure that those entries match what you typed in. So I'm routing UDP to port 53. I'm routing TCP to port 9040.
Okay. Cool.
Yeah. So I want to see that. If that says that, then I'm good.
Cool.
Now we have to save that. We have to make sure that it actually saves that table, because if I were to reboot right now, it would just go away and I have to re-enter it.
Default.
Right. So what I'm going to do is I'm going to save it by putting sudo. Actually, it's going to be sudo sh -c and then in quotations IP tables -save greater than /etc /IP tables .ipv4.nat close quotation.
So,
I don't want to type all that, so I'm going to cheat and use my handy dandy little text file over here.
yeah, that's the one thing you notice about typing things into terminal is that you have to be super exact and precise, and sometimes with these long URLs and things, it gets
It's really easy
tedious.
to mess it up, right? So just copy and paste it. We're showing you just so you understand how this works. So I've now saved that IP table.
Cool.
What I want to do now is I want to create a log file. Earlier in the config, I did tell it where I can find a log file. I could skip this, but I actually do want a log file. In case something doesn't work, I want to be able to go into that file and say, well, where did it break?
Right.
And in order for that to happen, I have to create the file, I have to change the ownership, and then I have to make sure that the Tor has permissions to write to the file.
Okay.
3 lines. These are actually very important if you're planning to play with Raspberry Pi, because they show off very important pieces of the management. The first one is sudo, so again, super user or substitute user do, touch. What touch does, touch creates a new file. It just creates an empty file. So I'm going to create an empty file at /var/log/tor. It's called notices.log.
Okay.
So it's just created that file. The second one is sudo chown. Chown is, it's a funny word that I just like to say, chown. But what chown does, chown actually sets ownership. So I'm setting ownership for that file to the Tor service. So the Tor service now owns that file.
Can write to it?
Right. And the last piece is chmod 644. This is kind of important just in general. Chmod tells them what can and cannot happen to the file. So if I put chmod 600, that means only the owner can read or write. Everyone else is locked out.
Oh.
If I do 666, it means everyone can read it, everyone can write. Yeah, it's basic, don't do that. Really, it's a bad idea.
Okay.
It means everyone has full access. 644 is actually a really good one. It's one I use most often. It means that the owner can read and write, everyone else can read but not write.
Okay.
So I'm doing 644.
Interesting.
So Tor will be able to read and write to the log, but anybody else, including me, will be able to just read the log. I don't want to modify it. I just want to see what's in there.
Right.
Okay. Now let's go ahead and start the service. Remember, I promised you I'd show you how to manually start a service. Here we go. Sudo service Tor start.
It's that simple.
It's that simple. Well, maybe it's that simple. Let's make sure that it's actually running. Sudo service Tor status. There we go. I want that in green. See where it says active running? So the service is running. If it was broken, if I didn't do it right, it would be in red.
Okay.
But because it's in green, it means I'm happy. Tor is now running.
Nice. All right.
We're not done yet, though.
We got to check it, though.
Well, we also need to make sure that it actually boots up.
Oh, okay.
So right now it's running, but if I were to shut down, the service would be there. It just would not start by default. I want to start it by default.
So on boot up, got
On
it.
boot up. So if you go back to my my terminal window, I'm going to put sudo update -rc .d tor enable. Okay, so I've just set it so that every time the Raspberry Pi boots, the Tor service will start up and the AP service will start up.
Okay, very nice.
Now what we need to do is, as this is so often the case, we're going to reboot our wonderful little device here. Shut down and reboot. Okay, while this is rebooting, let me explain what we've just done. Okay. We've allowed all of our traffic to go from the wireless interface to the Ethernet interface, but it's going to be encapsulated in Tor.
Right.
Okay. This is good because it can anonymize my location. However, you have to be responsible in how you use it. If you're using, say, Chrome in your regular mode, all of your cookies are still going to be transmitted through the Tor system. Okay, so if there's a web server on the other side that's examining cookies, they can still find out exactly who you are just by looking at the little fingerprints that you've left.
Okay.
Okay, so if you're going to use Tor, I typically use a perfectly clean browser. I won't even use a browser in incognito mode. I actually have a little USB pen drive that has a browser on it. And it's perfectly clear every time I start it up. But just know that you've anonymized and encrypted the traffic.
Right,
but
not
if
the
the traffic
cookies.
is still identifying you, then you've kind of undone the protection.
Okay.
All right.
That
All
makes
right.
sense.
So we've freshly booted. If we've done this right, this should be connected. Let's see our phone. Is our phone still connected? Yeah, our phone is connected to Know-How. So if I go back to a web page here, let's go to a different page. Twit. Let's go to Twit TV. There we go. And you'll notice it is a little bit slow.
Right. So some of the limitations I assume still with Tor is that the traffic can be slow, and there's certain websites that won't allow you to
Precisely.
access.
Like, for example, the Twit TV chat room.
Right.
Yeah.
Right.
Yeah. And again, because I'm adding a layer of complexity, of course, it's going to slow it down, but now it's much more secure. The question is it secure? Let's go back, because remember, we're still tapped
We're
here.
tapped, yeah.
So let's stop this.
Which is our kind of faux example of what the ISP would be able to see.
correct. So I'm going to go ahead and go back into this. It's still filtering for DNS, and let's see what happens. So Alex, if you come back to the overhead shot, let's go to here. So we've started the request. It's going out to the web server. It's going to start loading up. Okay. Now switch back to the Wireshark screen. Boom. Nothing.
Wait, is it supposed to be nothing?
Yeah. No. Well, it is, because it means that the DNS has been encrypted. It can't read DNS. If I remove the filter, hold on.
So you'll still see that traffic.
I'm getting
is
traffic.
going, but you don't know.
Yeah, because I mean, look at it. It's all
It's a
encrypted.
query,
Everything is encrypted.
That's cool.
Okay, so it's not getting it, even though all of this traffic is going through the tap. The tap is not recognizing the regular protocols like it could before it was going to the Tor. It just shows you it actually works.
Yeah, no, that's
So
a good
they-
way to double check, because sometimes it just feels like a magic box.
Yeah,
and
it's
you
like,
don't
oh,
know.
it's going slower. It must be encrypted.
must
Not
be working.
necessarily.
Yeah.
A tap's a really good way to check. So
Cool.
I actually have one of these on the link going out to the internet. So behind my router, or actually in front of my router, over to the cable modem.
Yeah.
So I can check to see exactly what's coming into and out of my network. It's the very first point of entry. In this particular case, I can use this to make sure that nothing is being transmitted in the clear. So I can scrub through all of my packets, and there are some bits of information. Like, actually, go down to the bottom here, Alex. Let me show you what I was talking about before. This is recognizing that it's Google Chrome. So obviously, my browser is not set for incognito mode, right?
Right.
If I want total obscurity, total security,
Yeah.
I would use a browser that allows me to like turn off everything, like identify itself wrongly. Like it will be Chrome identifying itself as Safari, and it will
Right.
turn off all my cookies, so there are no cookies being exchanged.
Yeah.
Again, security is more than just one cool device. Security is going to require you to do a little bit of critical thinking of what kind of traffic you're actually putting out there.
That's really interesting. And I guess, yeah, This would all kind of be for naught if you were just to use your regular Chrome browser with all your cookies and save stuff. Okay.
Because on the other end, remember, all the Tor network is it anonymizes where you drop into the internet.
Yeah.
Okay? So when you drop into the regular internet, the non-encrypted internet, it's in a different spot. So if someone's trying to just locate you via the node that you normally go out of, they won't find you there. Or if they're trying to capture the traffic that's coming out of your network, it's going to be encrypted. They won't be able to figure it out. However, if your browser is saying, oh, it's me, it's Father Robert, it doesn't matter what I did to anonymize the location. I'm still identifying myself at the far end.
I'm imagining it's like you put on a disguise or something like that. Like you're going out in public with a disguise, but it says, hello, my name is Father Robert Ballasare as like a name tag. It's like
Doing it that way is basically being an archer and saying, I'm a spy, by the way.
Yeah,
It's
exactly.
like,
I don't know if you've heard of me. Bond. James Bond.
All right. Now, this is not the end of this project. Again, as we mentioned, we kind of stepped this up because we wanted this, it's a good time to get into the public conscious about encryption and security. What I want to do with this is I want to be adding this. So this is a little touch screen that I got that it plugs into the Raspberry Pi. Okay, I've got a little coding. It's only 320 by 240, so it's really, really minimal resolution.
Still has the plastic on it, though.
That
will never come off.
See, look. See, this is old.
Oh my god, it's like brand new underneath that plastic.
Right? At least until I install it. I don't want to get scrapped up. Because right now, I'm limited to this being a wireless access point. So it goes from my device over the wireless into the Raspberry Pi over Ethernet out.
Right.
So there's only one way for me to do this. It's very simple to change it. I just use the interface function on this. And the interface allows me to switch which connection is part of which connection.
Okay.
Right. So what I want to do is I'm actually in the middle of designing a custom distro that just does Raspberry Pi Tor.
Wow.
So we do none of the steps that we just talked about.
You just plug it in.
You image it and you plug it in. But then what it will do is if you have this screen, it will allow you to, I'm going to put 2 wireless adapters and 2 Ethernet adapters, one over USB, and it will say from where to where. So I can go from wireless to wireless, from wired to wireless, wired to wired, or wireless to wired. And that will mean that I can use this device anywhere. I can go into
take it with you.
Precisely.
And then bring a battery for it or something.
Well,
make it portable.
the thing I'm building has a battery.
Oh.
It has like a 12-hour battery on it. So. Which is why I'm not using the 8-inch. I love the 8-inch touchscreen, but that thing sucks down power. This is nice and frugal with its power use.
Right, and size-wise, you won't have to lug around a bunch of stuff.
Precisely. But once I have that done, what it means is you'll have a little teeny tiny package that you just sit down, you plug it into your laptop. I would always use wired. I don't use wireless if I want security, because wireless is by its nature insecure.
Yes.
But I would go from, say, I could go into a Starbucks, plug this into my Ethernet jack, and then tell the Raspberry Pi, to connect to the Starbucks Open Wi-Fi.
Yeah.
But now I'm going Tor from my laptop through the Starbucks system, so anyone looking at my traffic will get it.
It's not going to matter. Yeah. Very cool.
Right? So that hopefully we'll get in May, because I've got a couple of projects stacked up between now and then.
No, that's exciting. I'm looking forward to that.
Yeah. Oh, does this make sense? I mean, there's a reason why we use the Raspberry Pi 3. Of course, it's going to cost you about $40. But once you got that and the SD card, which will cost you like $5, once you have that, you're done. There's nothing else you need for this project. This is about a $40, $45 project. And now you have something that is a turnkey solution. You plug it in, and it is Tor.
Yeah.
And the way that I have this script set up, if you follow all the instructions, is if Tor doesn't work, so if Tor disengages, it kills the connection.
Oh, instead of starting your broadcasting what you're doing on the internet,
precisely,
like unencrypted?
There are some other ways to do this. There are some auto scripts, which I like, that make them very easy, but it's set up so that if Tor breaks, it still keeps the access point going.
So you think you're protected and you're not.
That's no bueno.
Oh, okay, okay. And so we did this project, or you did this project on the Raspberry Pi, and the Pi is powerful enough for the Tor network and everything that you did for this project, but could you use like a different piece of hardware for this sort of thing?
You could probably go with like BeagleBone. A BeagleBone Black would work really well for this. You could not do this with an Arduino, not even a Mega. It's too much.
What about like an old PC or something like that?
Yes, but this would do it better.
Yeah.
There are limitations though, as you mentioned. I mean, I am slowing down already just because I'm adding an extra layer of complexity to my network stack. However, it's not just that. I'm also not going to get anywhere near a gigabit Ethernet.
Yeah.
I mean, there's just not enough power in the Raspberry Pi to push that many packets while at the same time doing the encryption.
So you're not going to try and do gaming while you're on the Tor network?
No. Not unless you like getting fragged. If you like getting fragged a lot, go ahead and use Tor.
Right. Okay.
Yeah.
Good to know.
And I think, yeah, actually, I'm very glad you brought that up, because you should start getting used to the fact that, like, I would never run Netflix through Tor. That's just, it might work, but on the civic side of me, I don't want to be the jerk that's mucking up the Tor network because I'm sucking down so much bandwidth.
Right.
That'd be a bad thing.
Well, I
So
guess
just
you have
be responsible.
You have to think of what are the things that you are doing that you necessarily wouldn't want people
Doing
or
your
IS
node, right?
Yeah.
Yeah, I mean, I'm using someone else's node. Actually, I'm using several other people's connectivity and nodes. So I shouldn't be that person who's using up way more than my fair share.
Right. And I mean, as far as like if you're gaming or you're doing Netflix, that's not a big deal. But if I'm doing like Google searches and I'm planning on going on a trip or something like that, I don't want, advertisers to be jacking up their prices on certain hotels that I was looking at, or plane tickets, or sending me, like, I just bought like a micro SD card and now I'm getting all these Amazon advertisements for buying SD cards.
Or like when I'm looking up instructions on making Ryzen to possibly disable a host.
I don't feel so good. That's weird. I'm going to have to call Comcast and start getting you tracked.
Make sure you toward.
Yeah.
Now, those segments were a lot of fun to film, not just because I got to deliberately infect computers, but I really liked that Tor project because it's something that I carry with me every day. In fact, I promised a more advanced version I will deliver probably once I finish the LiPi project, so we can have a Tor router that, you can customize as you go. Now, that's not the only thing that we did on Know-How. Yes, we did networking. Yes, we did security. But we also did a lot of 3D modeling. We did Grow-How, and we did a lot of coding. I thought maybe we should take a look at some of my favorite episodes from coding, specifically the episodes where we looked at reusing your infrared remote controls and when we were finishing up our Steampunk Goggles version 2. If you're a coder or if you're thinking about using Arduinos, this is for you.
So we've got a bunch of devices here that I've all jiggered to work on 12 volts. You may remember this. This was our 12-volt odor eater. It's a jar of activated carbon or charcoal that has a little fan so that you can put this like right next to the litter box, and it basically just eliminates a lot of the odors coming out. This was the fan that we used from the swamp cooler. We made ourselves a little home-built cooler last summer. These are some of the cyber goggles, and of course there's my little Google spinner. Just to show you that the code is still working, yes, I can trigger all of these devices just by sending the proper key. Now also, I've switched off to a relay that actually has all of the relays working. So right now, with just the setup I have got on the table, I could trigger 8 devices and turn anything on or off as I choose. And then also turn everything off. Oh, the reason why we did it this way, where I'm showing you how to use the keyboard, is because anytime you're developing a project in Arduino, and this goes to any of you who are trying to get into this world, you always want to start with something that's simple. And so something that's simple here is the ability to trigger via the programming console. So if I'm programming this Arduino, I already have access to a console. I might as well make it work this way. However, what we promised was that we were going to let you use your old IR remote to be able to trigger all this stuff. Let me show you how easy it is to do that. So if you go ahead and go to my computer, Burke, there we go. So this is a little bit different. We've added this, the IR remote, because we're now using the IR receiver that we used last week. So we had to put the library back in there. We added this because this defines the pin to which our IR receiver is connected, in this case, it's connected to pin 11. Then we have this. This turns on the IR receiver, and this creates, again, just like before, it's a storage space. It's a place for when the codes start coming in, it's going to put them into that. Okay? Now, this part you've seen before. This tells me where all of my relays are connected to. In this particular case, pins 3 through 10. This is the one that sets is the relay on or off. So if it's 1, it's off. If it's 0, it's on. And this is important because this comes at the start of the program. So when I first turn on the Arduino, everything is going to default to off. If I set this for 0, so if I changed all these number 1s to a number 0, every time I rebooted the Arduino, everything would start on, which probably not good. You don't want that, right? You want everything to default off. Now in my setup, This part you've seen before. I'm just setting my pin modes, just like we did in the last two examples. But this, it starts the receiver. It initializes the receiver. It says, hey, receiver, I'm going to start needing you. Make sure you're on. All right. So let's go ahead and move on. This part right here, again, this is what I love, super simple, the loop. This is the part of the program that will just keep happening over and over again. There's nothing in here except for calls to those exact same two functions that we had in the last two examples. This is what we want. You're building up little by little, incremental knowledge. And then when I go to the check input, this looks the same except this. In the last example, we had that the if statement, and the if statement said, if you receive anything from the console, from the keyboard, then do this. This is the same thing, except if I receive anything from the IR receiver. So instead of the keyboard, it's from the IR receiver, then do something. And instead of the ASCII code, so 48, 49, 50, 51, I'm doing this. These are the codes that are actually being received by the IR receiver. Everything else in this program, except this, and the parts that are specific to using an IR receiver, are exactly the same as they were in the previous example. So this is why that's important, because we don't want people to think, oh, wait, where did that come from? The only thing that's different is what I'm comparing each of these case statements against. All right, so let's go ahead and load this up. Let's make sure we're going to the right thing. We're going to an Arduino Uno. We are going to port 5, and let's send it. So it's going to compile the sketch, and then it's going to upload it to my Arduino. And if I've done this right, I can go ahead and start pressing buttons on this remote control, and then we can see what's actually coming in.
How do you know which buttons to push?
Oh, well, because I'm defining them.
Okay.
All right, let me actually, very good question. Let me show you that. So let's go ahead and go here. We're going to go open up my serial monitor, and I'm going to start by pushing, let's say, the volume up button. And that's the code that gets sent on the volume up button. But it doesn't do anything because there's nothing here that uses that code.
Right.
That code doesn't exist in my case statements. And remember what we talked about. If it doesn't exist in the list of case statements, it just doesn't do anything. So, and I can do that for a bunch of them. So if you go back to that screen, this is what the mute code looks like. Here's what the source code looks like. Here's what the menu code looks like. None of those do anything. However, let's look at this. What's the very first code here? Case 40BE807F, which, hold on, let me do this. If I push the number 1, that's the code that gets sent, 40BE807F. And if you go to the wide shot, Burke, you'll notice I can now trigger all these devices just using the keys on my remote. So, and actually, to further prove that, I'm going to go ahead and yank this. So this is the cable connecting it to the computer. So it's no longer connected to the computer.
Cables.
The only thing coming into this is an external power source. So a 12-volt power source, which powers everything. And I can turn everything on and off to my heart's content.
So on and off are the same buttons.
Right, so here, actually, I'll give that to you. So let's say, actually, hit 2. The receiver's here, 2. Okay, 3, 4. Okay, so I like that one, 4. So hit 4 again. So every time you hit 4, it's either going to turn it on or off. So remember, if it's on, turn it off. If it's off, turn it on. And if you hit 0, I added one more case statement, that turns everything off.
Everything
That's the
on.
smash.
But it doesn't turn everything back on.
No, because, well,
Sad.
I could do, actually, if you want, thank you. See, Megan, you got such great ideas. We're not using the number 9 because there's only 8 relays. You're doing that a lot.
I really am.
We're only using 8 relays, but I could add, let's go ahead and add one more case statement.
Okay.
To say, turn everything on.
Yes.
Okay, so let's do that.
Turn everything on.
You've got great ideas, Megan.
Turn all the things on.
Turn on all the things.
Turn on all the things.
Okay, so the first thing we need to do is we need to find what code that is. So point the remote at the IR receiver and hit the number 9.
9.
Okay, so that's the code. Remember, FFFF, that's what happens when you hold it down. It just repeats. Okay, so that's 40BE906F. That's the code I'm going to have to program in. So let's go to the bottom of my software here. This is the all off. And that was on 40BE00FF. So what I'm going to do is I'm just going to copy that. Control C, Control V. And I'm going to go ahead and create a new case statement using that code. So if we go back over here, hit 9 again. There we go. So this code, Control C, Control V. So I am now telling it, if it sees that code, do the thing below here. And I'm going to put all on. And I'm going to switch this number to 0, because 0 means on. Oop. Oop.
Oop.
There we go. And that's it. So
Okay.
if I've done this right, let's go ahead and upload this. If I've done this right, it means that now you can hit 1, 2, 3, 4, 5, 6, 7, 8. And those will turn on those individual relays. You can hit 9, which turns everything off, on, and 0, which turns everything off. And so go ahead and there you go. And now hit 0 to turn it all off, and hit 9. And it turns everything on. There you go.
You did that so quickly.
Yeah, that's what I like about this, because once you've got an Arduino controlling this, it's all software. Everything can be custom.
It's as if I never used a remote before, but it's exciting because we did it.
Exactly, we did it. And look how many keys there are on that remote that you're not using. I can have that trigger combinations. I can say, hey, you know what? If I hit the mute button, turn on 1 and 6 and turn off 5. So it's all about what you have it connected to and what you want it to do. But once you've got this wired in, everything can be set in software, which is what I love, because once I'm to that point, it's just me customizing. It's like how you customize your phone, right? I can customize what my software does because I know that the hardware is already working. Hey, Brian, you ready for some coding?
I'm ready. I've prepared my mind and my body for some coding.
All right, let's go ahead and jump on in. This should be familiar. This is the Arduino Sketch environment. Now, we've done a couple of things. We've included one library, Fast LED. That's the library that lets us access WS2812 LEDs.
Yep.
Gives us all the cool commands and shortcuts so that we can make it do what we want it to do.
Oh, we've seen that before.
Oh, we have. And we've also seen all of this. So remember, I like to define and put my variables up top, just so that I know what are the variables that I can play with.
That's just good coding.
That's just good coding. So I've got data pin 3. That's the pin to which I'm going to connect my WS2812 string. Because remember, I'm going from one LED ring to the next, so all of them are one string. So 16 LEDs each. I've got 32 LEDs in the string.
That makes sense.
Okay. I've also got this, the number of LEDs, that's 32. I've got the brightness. Right now I have it set for 100, and the reason why I have it set for 100 is because I could go to 255, but you make it brighter, you use more power.
Right.
And also, typically the place where you use these are indoors, like in conferences. 100 is plenty bright. You
I
go
was gonna
200,
say,
it's just overpowered.
even under the studio lights that we have right now, it's plenty bright.
Right, I mean, look at this. So this is set for 100. It's not like you can't see that.
No,
but if you
perfect.
if you go much higher than this, it just becomes, especially on our cameras, it's just
Blown
a
out.
blob of light. It's
Yeah,
blown
no,
out.
it looks good at 100. So.
Right. So the other thing that you want to know is this, the speed. So this is actually, the number that you put here is, in the delay, it's going to be divided by this, 1,000 divided by this number. So the higher you make this number, the less delay there's going to be.
Okay.
The less delay there's going to be, the faster the animations are going to run.
Okay.
All right. Now this is new. This is specifically for my warp core animations. Remember how if I'm going to use a value multiple times, I like to have it as a definition rather than typing in that value multiple times.
Right. So then if you want to go back and change it, you don't have to do it like 100 times.
Precisely. I don't want to have to change it in the 20 different spots.
Right.
Because I might forget one and suddenly it looks weird. This way, as long as I use these values, the warp red, warp green, warp blue, wing red, wing green, wing blue, all of it will look uniform.
Very nice.
And I can just change it in one place and it changes it for the entire animation.
Perfect.
All right. So the other things that we're going to do is, right below here, this is the function that is going to be called that reads the potentiometer. So in the original 100 lines example that we used for the steampunk goggles, all it did was cycle through the animation. So it would run an animation for about 10 seconds and then move to the next, and the next, and the next, and go back to the top of the list.
Right.
I wanted to make it so that you could actually select which animation that you wanted to use. So what I did was this. I did an A read, which is an analog read, of 7. So I'm reading pin 7, analog pin 7, which is connected to my potentiometer.
Right. So it's getting the signal from that. Got it.
Right. That is going to bring me back a value between 0 and 1024.
Okay.
Oh, actually, it goes all the way to 1200, but
But
1024 is.
you've bracketed it out to 1024.
So what I'm going to do is that gives me my value, but then we've added this. This is a range check. Remember how we talked about how this is important? Because every once in a while, if you've got a flaky potentiometer, it will go down to less than 0, and it will go above 1024.
Right.
Which we don't want, because if it's out of range, weird things happen. Most likely, the Arduino just freezes up.
Right.
So what I've done here is I've actually told it, if it goes down below 0, set it back to 0. And if it goes above 1010, set it to
back to
1010.
1010,
So
yeah.
absolutely guaranteed it will not go out of range. It can only go down to 0. It can only go to up to 1010. So even if something funky happens on the potentiometer, it's not going to crash the Arduino out.
Cool. And so the next step is then bracketing out the different patterns between.
Precisely, because going between 0 and 1010 doesn't help me a lot in choosing one of 10 different patterns.
Right.
So what I've done here is I've used it's a built-in function, we've seen it before, called map. So my PAT choice, my pattern choice, is the map function run on that value I just took from the potentiometer and range checked. So from 0 to 110, because remember, that potentiometer goes from nothing, from 0 all the way up to 110, and because I've range checked it, I know it's only going to be that.
And then you do 0 to 9.
Precisely. So it does all the math for me. So it divides the range up into 10 pieces, and it says, okay, as long as you're within this and this, it stays at number 1, this and this is number 2. It does that for me.
Nice.
Which is nice. Okay, and the reason why we have 0 to 9 is because 0 is also a value, so it's 10. It's
Right,
0 to 9
It is
10 values.
10, but
It is actually 10. Below this, these are the 10 different animations that I can choose from. So blank is the one that I wrote just so that it slowly goes off to off.
Right.
Then I've got rainbow. It's the standard rainbow pattern. And
It's pretty.
Yeah, we've seen these all before until we get down to warp core. So warp core is new. And I created this again for the 3D printed warp core that I created for my room. All this is going to do is it's one of these, it's a follow. So it says, okay, where are you? Move one up, move one up, move one up, move one up. Every time it runs, it's going to move it to the next position.
Right. And it's the one you have running right now, isn't it?
Actually, the one that I'm running right now, this is the dual warp core.
Oh, dual warp.
Yeah, so the single warp core looks like, let me move it back a little bit. So that's the single. So this is the code we're looking at right now. What it does is imagine these two LEDs, or these two were on a single strip of LEDs. So what they'd be doing is right now they would be converging. Right.
That
so
makes sense.
That's the warp core. When I go to the double, imagine this, but there's LEDs on both sides. So now it's doing it, so you can see it.
Yes, and it makes this noise too, right?
Yeah, absolutely, of course. So if you look at this, all that this is a series of if statements. It's if it's less than 0, then move it up. If it's greater than a certain level, then move it back down.
Okay.
Right? And I have warp core, and then I have warp core 2, and this is the dual-sided. These use, as you see, wing red, wing green, warp red, warp green, et cetera, et cetera.
These are the ones you defined up above.
Top. So if I change that, I can completely change how the animation looks. In fact, let's do that right now.
Don't do it. It's perfect the way it is.
Let's go ahead and plug in.
All right, fine.
Boom. There we go. We've frozen it. Okay. And let's go ahead and send it to COM4, and we're going to send it to an Arduino Nano. And what shall we change it to? So right now, if you go up to my code, Alex, I've got warp red of 0. So there's no red.
Yeah.
There's 100. So about half, less than half of it is green, and then all of it is blue. So let's reverse this. Let's say no blue and all red.
Yeah. 255.
And let's change this to no red, no blue, and all green.
Yeah, sure.
That?
Oh, will that can we make it look like the goggles in Jurassic Park? I guess if they were all green.
Yeah, actually, yeah. We just have to color match it. So it's going to compile it. And as soon as you see it freeze, it means it's going to be uploading. It's going to take a while because it's a new build. And God, there we go. Uploading.
That's the noise uploading makes, I'm pretty sure.
Well, no, there we go. So we changed the color. And because we use these definition of this variable down below, I only change it in one spot and the entire animation changes.
That is cool.
So much easier than trying to rewrite it every time you want to change the color.
I like it.
Yeah,
I like
so
it
this is
a
getting
lot.
closer to Jurassic Park, but I think we'd have to get rid of the red entirely.
Yeah, we have to get rid of the red, and then let's see. Let's go back to the single. Yeah, that's pretty cool. You might have to change the animation a little bit to make, because I think it's spaced out a little differently. But
Yeah, I don't think they show every LED. It's like every fifth LED.
yeah,
and it just
and
goes
then,
around
like,
and around.
spins around.
I mean, we can make these. I mean,
We'll make
if you want, I'll do that for you, Brian.
No, I want to give it a shot. Yeah, okay, so it's 4 and then rotating around. Okay.
Right.
I want to work on that. I'll try it.
Okay, so let's go ahead and take a look at the setup and the loop. Remember, this is the part where we set up the program the way that we're going to use it. Setup is super simple. We've seen this before. If you use WS2812s, it sets up the array. So remember how WS2812 works is it creates an array. You fill that array with values for red, blue, green.
Right.
So every light has a red value, a blue value, and a green value. So I fill that out, and then I do the send. So I send it down the line, and every LED will take 3 bytes, representing the red, the blue, the green,
And then pass it down.
pass it down the line.
Yeah, for as many LEDs that you determined.
Precisely.
Which 32 in this project.
And then my loop, remember, we want the loops to always be small. The loop should be very simple. It should call functions. It shouldn't have a whole lot in it. This is pretty dang small. So this first one is going to run the animation pattern. The second one is going to cycle the base color for the rainbow, because any pattern I have that uses rainbow, I need something to say, okay, change the color of the rainbow.
Change the color of the rainbow.
Yeah. This actually checks every half second. It's going to call the potentiometer function that I showed you up top.
Right.
And it's going to say, what's your value? If the value changes, then it changes the pattern that it's running.
Okay.
And then down below, this is the super simple one. Once it's done all that, show the LED and then delay. And that delay is important because if I have no delay, it would just look like a bunch of really, really fast blinking lights.
Yeah, you wouldn't be able to discern it from the other one. Yeah.
Precisely. Now, Brian, next week, we're going to go ahead and we're going to sit down, we're going to solder these, we're going to put it together entirely in real time so people get a sense of how difficult it is. This is actually not a difficult project. It's
Once you have
fun.
all the pieces together.
One thing I do want to change, though, is
What?
I've always wanted a potentiometer for brightness and a potentiometer for speed, because you saw I can control those.
Right.
Brightness and speed.
Yeah.
I could do the same thing with a potentiometer. But the problem is this frame isn't big enough to have another potentiometer like this one.
Right.
So what I'm going to do is I'm actually going to use the cart system. I'm going to put 2 very small potentiometers, the screwdriver ones, the tiny little ones, so I can open up the back and adjust animation speed and brightness.
Oh, okay. Yeah, I like that
But,
idea.
just on my version.
Just on your version? Oh, we'll see about
Mine
that.
has to be a little bit better than yours, Ryan.
I'm wondering too if you could make like just an indent or like a little, and then have part of the gear extruding out, and then just use it as like an up down, like kind of almost like a volume slide for brightness.
I actually started out doing that.
Yeah. Is it really hard?
And well, the problem is it cuts into all the space I needed for my Arduino.
That makes sense. And you wouldn't be able to use the cartridge system with
Yeah.
that either. Yeah.
This I kind of like. Seriously, the cartridge system is probably the coolest upgrade here because it really makes this flexible. In fact, if you look at this one, this is my super secret prototype version. This actually uses there's a mini breadboard in there.
What?
Yeah. So actually, it's kind of tight.
yeah.
You can't really see it, but yeah, there's.
I believe
So there we
it.
go. See, there's jumpers.
Oh yeah.
So I can very easily change the wiring on this one. I designed it that way, and
Yeah.
I kind of like that. It gives me the ability to have a finished product, but at a moment's notice, I could just change everything if I don't like it.
Well, whatever happened to you were gonna do steam coming out, right? Like using some sort of vapor system. Could you do one that has a battery and that, and then hot swap it basically?
It totally works, except one time it caught on fire.
Oh, well, you got a battery strapped to your head anyway, so why not?
Who would have thought that putting a semi-flammable liquid in contact with a broiling hot coil could cause fire?
You don't know until you do it, right?
I will say it worked really cool for about 15 minutes. The problem is the coil needs to stay submerged in the fog liquid. When the reservoir ran too low,
then
it just started.
It started making a lot of
It
smoke.
melted the frame.
Oh wow! Yeah.
And someone's like, hey man, your goggles are smoking. I'm like, yeah, they're supposed to. Goes, no. I think they're like on fire.
Like in a bad way. Those goggles are smoking hot.
And so I figured, fire lithium-ion batteries strapped around your head.
Not so
Probably
good.
Not a great
Not
idea.
so good.
That does it for our best of 2017 for Know How. I do want to say that it's been an absolute privilege, an honor to host this show for you, to be with some wonderful co-hosts who have brought their knowledge, their vision, their passion to the show each and every single week. It's because of you and because of your support that we get to keep doing this. And hopefully we'll continue to do it into the new year. Now, if you want to know more about any of the projects that we covered, about any of these episodes, so you could go back and watch the full thing, make sure to go to our show page at twit.tv/KH. There you'll find all of our back episodes as well as the show notes so you can follow along as we do projects, so that you can purchase the individual parts that you need to make our projects. And yes, to subscribe. It is the best way to support the show. If you want Know How to grow, to continue, then share that subscription, audio, video, or high definition video with your loved ones, with your friends. Get everyone into the maker movement because that's where we live. Also, don't forget that you can find us on the socials, specifically in Google+. Just go to Google+, look for Know How. There's a very short approval process so I can keep out all the spam accounts. But once you're in, you get access to almost 12,000 Ketas. Those are our know-it-alls, people who are in every stage of their maker journey. And it's just a really good way to share what you're creating or maybe share your knowledge. Jump in, post pictures of your projects, ask us questions. We'll try to get you into a feedback episode in the future. Finally, thanks to everyone here who makes this show possible. Of course, to Lisa and Leo, to my co-hosts, Patrick, Jason, and Megan. And yes, to the third member of every show, I'm going to call him by his real name, Alex. Alex is a fantastic guy. He has been with us forever. And Alex, do you want to say something to the folks at home so they can have some holiday cheer?
Excuse me, Padre. It's pronounced Alex. Oh, wait.
Wow. Yeah, this is uncharted territory for us. Huh, go figure. Until next time.
Hold on, Padre. I got to just get this out of here.
Bye, Leo. Until next time, folks, thank you so very much. I am Father Robert Balaser, the Digital Jesuit. And now that you know how, go celebrate.